Good afternoon, everyone, and welcome to this session of UM6P Science Week. Today, we are diving into a theme that sits at the very heart of our global and national energy transition. Is there truly a really bright future for green hydrogen in Morocco? As the world seeks to defossilize, Morocco is positioning itself not just as a participant, but as a strategic leader. From industrial applications and scientific breakthroughs to the complex geopolitics of energy corridors, the next 3 hours are dedicated to unpacking the reality behind this ambition. To kick us off, we begin with the foundations, the science and the national vision. We will look at how hydrogen is produced, its current industrial footprint, and how UM6P is driving the talent and innovation needed to sustain this industry. It is an honor to invite on the stage a man who needs little to no introduction in these halls, Professor Abdelsamad Fayek, who is a full professor at UM6P, Director at UM6P, and R&D Director at Innovate for Industry, IFI. With a PhD from the University of the Basque Country, a career spanning leading institutions like the German Aerospace Center and CIC Energy Gun, he's a globally recognized expert with over 180 publications and 7 international patents. Professor Abdelsamad Fayek, under applause, the floor is yours.
Good afternoon. Thank you, Kausar, for this nice introduction. Really, I am very happy to be with you today to discuss about this interesting subject for Morocco, but also for the world, how to shift from the fossil fuel-based energy system to a renewable future. Today, I will speak about green hydrogen in Morocco, vision, science, and industrial uses. But of course, as we have other lectures that will be provided after my lecture by Professor Heino von Meyer, I will just give just a short introduction how we can use hydrogen in different industrial sectors. But of course, Professor Heino will go deep in these subjects. Okay, this is the plan of my presentation. I will start first by a small introduction. Second, I will just to give you an overview why hydrogen, and also to discuss about how we produce nowadays the hydrogen at industrial scale, and how what is the impact of this method that we are using nowadays, and what is going to be the future of hydrogen in general. And then I will move to give more details about the electrolysis technology that is considered as the most promising technology that can be used to produce green hydrogen. I will discuss about history and where we are now. And then I will give a general overview about some few applications where we can apply green hydrogen. But of course, this part will be extended by the second speaker, Professor Heino von Meyer. And at the end, I will discuss about challenge opportunities, and I will finalize by conclusion and perspectives. As introduction to my talk, I want to share with you these 2 investments plan. That's the 2 big investments that we have in Morocco. The first one is led by OCP Group, and where is aiming to produce 1 million tons of green ammonia in the horizon of 2027, and of course to arrive to produce 3 million tons of green ammonia in 2032, with a dedicated budget of $7 billion for this plan to promote green molecules. When we are speaking about green ammonia, you are asking yourself, what is the connection between ammonia and hydrogen? Later on in my presentation, you will have a clear idea what means ammonia and what means hydrogen, and why when we are speaking about green hydrogen, we are speaking as well about green ammonia. We have also the other big project led by the government of Morocco, where they receive many offers from different consortium. The main ones are 5 consortium that they present to develop 6 projects in Morocco. And as you can see in the picture, I will not discuss about each consortium, but all these projects are aiming to produce green ammonia in Morocco or to produce industrial fuel, what we call e-fuel, and also this e-fuel is connected with green hydrogen, but also, for example, the consortium of Nariva or Aqua Power, you see that they are aiming to produce green steel. That means we can use hydrogen to decarbonize the sector of the steel and to produce green steel instead of having the classical way how we are producing steel. And we have a lot of impacts on the atmosphere by producing a lot of greenhouse gas that is just thrown to the atmosphere. Okay, when I share with you these very promising projects of Morocco, of course, we need to ask some questions. Why Morocco? Why Morocco, who wants to be a hub of the green hydrogen technology? Why Morocco is aiming to do all these kind of investments? Maybe can be many reasons behind that. Why? Because we have like some kind of exceptional renewable resources. We have solar energy, we have wind, we have hydropower. That means that is very attractive to do this kind of business, as you will see later that this kind of developments are energy-poor, that they consume lots of energy, and we need a source of renewable energy, and this energy should be in form mainly of electricity. Strategic location, this is also a very important point for the project of Morocco. We are close to Europe. That means if we are producing here, that we have a market close to us, but also we have a good connection with Africa, where also still we need a lot of sustainable energy and sustainable molecules. Reducing the energy import dependence. As you know, Morocco, we are importing more than 90% of our energy from abroad in form of fossil fuels like petrol or coal or so on. That means instead of relying on to import like our source of energy from abroad, to produce them locally. This is also a very important point. We have also the strengthening the chemical sovereignty. That means later on with my presentation, we will see that from green hydrogen, we can synthesize many kind of green molecules. That means also can be imported from Morocco, or also to decarbonize some Moroccan industry that we call that's hard to decarbonize, like the steel industry, iron and steel industry, among other kind of industries. Second question is about why green ammonia? Also, that in the project that I presented to you before, all of them are stressing like a green ammonia, like a great molecule. And why green ammonia? Because maybe we have in Morocco OCP's leadership in fertilizer worldwide. This like maybe can be the reason. Or ammonia also can be used for other kind of application to store or transport hydrogen in short term. And also the question of that we have worldwide a matter infrastructure concerning the storage of ammonia, transport of ammonia via ships, and also are available in the ports, or to decarbonize, for example, some kind of transport like maritime transport or also the airplane transport. Why we don't decarbonize via the molecule of ammonia? We see that. I will hope that with my presentation, you will have a clear answer by yourself regarding this question. If not, in the session of KI, I will be happy to answer to your questions. Let's start from the scratch, because as the audience is very large, you are familiar with that. This is the periodic table. That is the universal map of all known chemical elements. Most of them are natural, but some of them that we are producing them via acceleration, like the one that of the uranium family. But as you can see here, this periodic table is having all the elements that you have in your mind, like iron, you can see it here, cobalt, nickel, any kind of element that you think about is in this universal map of the elements. And these elements are classified according to their atomic number. That means each element, if you see the manganese is having 25 atomic number, iron 26, other one 27. What that means, that in the nucleus you have the protons, you have 26 protons, and you have the electrons that are rotating surrounding the nucleus. And if you see this table, you see that the hydrogen is the first element. That means it's having just one proton. This is very important. Why? Because when we come to the next slide, you will see that the hydrogen is the smallest atom that we can have, because it's composed by just one proton and one electron. And of course, when we speak about hydrogen gas, when we are speaking, because we should differentiate between hydrogen element or hydrogen atom and hydrogen when we speak in the energy context, when we, at that moment we are speaking about hydrogen gas. That means H2, is not ash, that we have on the right side of the slide. What means that? That means also the hydrogen is the less dense of all gases. That means if you take any kind of gases, hydrogen is having this small molecule because it's composed by two small atoms. And from where is coming the name of hydrogen? Hydrogen is coming from a Greek word. That's hydro is meaning water, and gen is creator. That means at that moment when they give this name to the hydrogen, they were thinking that hydrogen is part forming the molecule of the water. When we come to the abundance of these elements, why also is very important, because we have the normal matter is composed by more than 75% of hydrogen. Even in our body, we have lots of hydrogen. In water, everywhere that we have hydrogen, that is present as atom. And when we come to the question of the energy, when we speak about hydrogen gas that we have on the right side of this slide, is having the highest gravimetric energy density. We are speaking about 120 megajoule per kilogram. If we compare it with natural gas or gasoline or coal, is almost 2 times or 3 times compared to the gasoline or natural gas, and even is more, is 4 times up to 4.5 times compared to the energy that we can extract when we are burning coal. That means from the energetic point of view is a very important fuel or molecule that we can use to decarbonize many industrial sectors. The question that we need to answer first, if it's possible to find natural hydrogen, like when we speak about petrol, fuels, fossil fuels, we speak about natural gas that we can find underground, but the question if it's possible to find hydrogen underground. Of course, we can find it in the atmosphere, but it's hard to take. But from the underground, if we can have some kind of big reserves that can help us to use this molecule or this in many industrial applications. To answer to this question, I share with you the first discovery of the hydrogen underground. It was in a very small village in Mali that we call it Boraki Bogo. And in the years 1987, the people there, they were drilling a well for water. And when they arrived to a depth of 112 meters, they suffered a big explosion. And at that moment, they didn't understand what is going on, and they decided to close this well for the safety of the people. After that, companies were coming to explore what's gas coming from the well, and the company Petroma, they identify that in this well, they have hydrogen coming as gas with a purity of 98%, as you can see in this right high panel. And of course, having like 1% of nitrogen, 1% of CH4, not NH4, sorry for that, is the methane. And from that moment, they decide, okay, it was like not a big flow, that means, and they decide to install an engine to produce electricity for the local community that they have there. And what is very attractive in this finding, that now we are speaking about since 2011, when they installed this engine there to produce electricity, that the flow of the gas or the pressure of the gas was maintained during 25 years. That means is sustainable regeneration of this hydrogen underground. And after that, they do many kind of exploration. And in 25 ways that they drill close to this area, they confirm that they have a hydrogen underground. But we are speaking that even that is very small, is modest discovery of hydrogen. It's not like natural gas that we find with a huge quantity in many parts of the world. Hydrogen there was just small reserve or small quantity. But this is very important because this is an emblematic discovery that was driving a global interest to look for natural hydrogen underground everywhere. Just not in this area, but everywhere to look if there is possibility to find hydrogen underground. And after that, I would like to explain to you why we can have hydrogen underground. We can have different kinds of mechanisms similar to the ones of the production of the petroleum that's underground or the oil underground. That means you have some kind of cracking of organic molecules that can lead to natural gas or can lead to oil or can lead as well to the hydrogen. Or also we have the other mechanism that is relying on the hydrogen that is making part of some kind of rocks underground, like hydrites rocks, and with the continuous diffusion from these ones to the top, we can have the hydrogen is coming. But we have other two mechanisms that can lead to big reserves of the hydrogen when we are speaking about radiolysis. That means we have some kind of radioactive elements like uranium, thorium, that's cracking the molecule of the water to form the hydrogen. Is this one on the left, unfortunately, this one. That means we can have this kind of mechanisms. It's a radioactive mechanism, but we have thermolysis. Thermolysis is the most promising one. What means thermolysis? That means when you have the superposition of two types of rocks, one is rich in water, and the other one is having iron-rich rock, like the olivine. And as underground we have good condition of temperature, pressure, we can generate the hydrogen. But generating hydrogen underground cannot solve the problem, and we cannot lead automatically to big reserve of the hydrogen. As I told you before, the molecule of the hydrogen is very small and is penetrating, is going up by diffusion. And sometimes you have like this, what we call Faraday circle, that are indicating that the hydrogen is coming from the underground, but is not trapped. To have the condition that this hydrogen can be trapped, we should have some kind of salt layers or caverns. Why salt? Because salt is making a very thin layer that's not allowing to the hydrogen to diffuse to the land. And like that, we can have some trapped hydrogen at the middle. And if we drill here, by consequence, we will have a reserve of hydrogen. After that, we start to have many kind of discoveries or exploration worldwide. We have some areas that is marked in green dots or green circle on the map, indicating that we have a free hydrogen. That means the hydrogen is coming and going to the atmosphere. We cannot trap it. We have some areas that is in red color that is trapped. That means we have some caverns that from there we can do some kind of exploration, exploitation to take it to the ground. Or we have what is corresponding to the blue dots that is dissolved. That means we have some hydrites, rocks underground, and we have a slow diffusion of the hydrogen to the surface. And after that, we start to have many companies worldwide that they are exploring to find the natural hydrogen, or what we call geological hydrogen, or also we call it white hydrogen. And we have for example, in USA that they are exploring many ways to check about the possibility to find hydrogen. In France, Australia, Mali, but also in Morocco a few years ago, it was a signature between Height, Swiss company, with the government of Morocco to explore the possibility to find hydrogen in the southern region of Morocco. Then, in 2020, 25, we were having like two big announcements. One coming from the United States that they thought that they discovered some wheels with the hydrogen, and they declared that the hydrogen is having there, that they having high purity, is around 96.1%, not like the one in the Mali that we see that is having 98%. And after that, in France, they are speaking, the Geo Resources and CNRS, they confirm a major underground deposit of 46 million tons that with an estimation of the economics of this, if we do the exploitation of these wheels, about $92 billion. This is just announcement. We don't have any kind of confirmation about these reserves from a technical point of view, and also is the way how to extract this, because sometimes we can even, with confirming like big reserves, there are also a process how to do exploitation of the site and how to get commercial benefit from it. My message here, or to take away, that even that natural hydrogen appears promising, but large-scale exploitation remains uncertain up to today. Then, when we are speaking that we don't have any natural hydrogen nowadays, okay, from where is coming the hydrogen and what is the quantity that we are producing worldwide and for which purpose that we are using? If we return back just to 2024, the last statistics that we have, we are producing or using more than 1 million tons of hydrogen. This hydrogen is mainly produced by fossil fuels. Later on, we are going to see. And why we produce this hydrogen? Because we need this molecule for many industrial applications. First, 25% is going for petroleum refining. That means when you are hearing the hydrocracking of the molecules that we are getting from the oil, we are using a hydrogen to do this hydrocracking. We have 10% that is going for methanol production. That you know that this element is very important for many industrial use. We have 55%, the big part is going to ammonia production, and others is going for many other kind of industrial application like transport or even in the agroalimentary industry. That means we have this molecule is needed for many industrial sectors, but unfortunately we cannot find it naturally. We cannot take it from the underground. That means we need to produce this molecule. Why 55 of the hydrogen is going to the ammonia production? This is why we are going to see in the next slides and why this ammonia is very important. Ammonia is different to the hydrogen gas that we have two atoms are bonded together to form the gas of ammonia, but we have is composed by one atom of nitrogen and 3 atoms of hydrogen. And you can see the structure in the middle, and at atmospheric pressure and temperature is in form of gas, is not liquid, and is a colorless gas. And if we want to have the liquid, because the boiling temperature of the ammonia is minus 33.5 at atmospheric pressure, we need to decrease temperature to this one. And this one, at this case, we will have liquid ammonia. We are speaking about anhydrous ammonia, not aqueous ammonia. We should go to this one. But of course, in industrial application, we are increasing a little bit the pressure to go to a temperature around minus 28 or minus 24 degrees C. And if we consider from this safety point of view, this molecule is not highly flammable. That means is well handled by the industry in safe way. Here I am sharing with you the evolution of ammonia production since 1900 to 2020. And as you can see here, something like very will attract your attention, that before 1920, we were not having any production of ammonia, because at that moment, the method how to produce it was not discovered yet. We'll see that later. And since 1920, the production of this ammonia is going up, of course, with some kind of fluctuation. And if we come to the year of 2023, where we have some statistics about the production of ammonia, we find that 240 million tons, huge amount of ammonia is produced worldwide. Why? Because we need this ammonia for many industrial applications. We have, of course, 68% of this ammonia is going to produce fertilizers because it's considered a source of nitrogen that we need for plants. 15% for nitric acid and explosives, 10% for refrigerant, and 7% for pharmaceutical and textile applications. We return back to this number of 68% that is dedicated for nitrogen production. And there you see the amount of the ammonia that we need in this sector is around 163.2 million tons. Why we need ammonia? Because in the field of the fertilizer, for the persons are not familiar with this field, to grow any kind of plant, we need to have like mainly three elements: nitrogen, phosphorus, potassium. Phosphorus, you know that OCP is a leader in the world to produce DP, but of course also is using ammonia to produce different kind of fertilizers that are based on P or with M or with K, or three of them that you hear NPK fertilizer. And the common ammonia-based fertilizer, we have urea that is solid, is easy to apply, and is having the main advantage, highest nitrogen content, and is also easy to handle. We have ammonia nitrates, we have urea ammonia nitrates, we have ammonium sulfate, the ammonium phosphate. That means the ammonium phosphate, for example, is having the P and M at the same time, but also we have NPK that is having the P, N, and K. And just to give you an idea about the group of CP is importing 2 million tons of ammonia, gray, not green. Later on, we'll discuss what is the difference between gray and green, but 2 million tons of ammonia per year to use it to produce solid fertilizer or liquid fertilizer here and to sell them later to everywhere in the world. As I explained to you before, that before 1920, that we didn't see any kind of production of green ammonia. Why? Because at the beginning, they were discovering some trace of aqueous ammonia in Libya at that moment, but unfortunately, it was not possible to find a big reserve. That means we should synthesize this ammonia at industry, first in laboratories, and from there we're starting many kind of research to have the method that to master how to do the synthesis of ammonia. Of course, to do synthesis of ammonia is you can see the equation here that we need 1 molecule of nitrogen, 3 molecules of hydrogen, and we are able to produce ammonia, but it's not spontaneous reaction. That means we need to have the right condition of pressure, temperature, and also catalysts that can allow us to do the synthesis of the ammonia. And as you see in the bottom part of the slide, we have 2 Nobel Prizes that they get for the discovery of the method to synthesize the ammonia. The first one was developed by Fritz Haber in 1909, and he won the Nobel Prize of Chemistry in 1919. He made the basis or the theoretical basis on the synthesis of the ammonia. What are the right conditions, the catalysts we can use, the pressure, temperature that will allow us to produce ammonia. And then later was coming Karl Bosch, that he was enabling the large-scale ammonia production. That means he moved from laboratory to industrial scale, and also he gets a Nobel Prize in Chemistry in 1931. So, to do synthesis of ammonia, we need 2 elements. We need nitrogen gas and we need hydrogen gas. And after that, we can do a synthesis via Haber-Bosch process. So from where normally coming this nitrogen and hydrogen? We'll come to the first one, nitrogen. We have it in the atmosphere. Here you see the composition of the air. We have more than 78% of nitrogen is in the green color. We have oxygen and we have other kind of gases. So in this case, to produce nitrogen, we can produce from the air, by the separation of this nitrogen from the other gases. Of course, we have different kinds of methods like cryogenic distillation, pressure swing adsorption, PSI we call it, or membrane separation. But the most used one is the one in the right side, in the left side. That means we need to cool the air at temperature around minus 196 is the temperature where we have the nitrogen in liquid. And as the air or as the oxygen having a higher temperature of liquefaction, that means we will have the other gas in form of gas, but in this case we can trap the nitrogen and we can separate from the other one, is the most common used method nowadays worldwide for the production of nitrogen. So for the production of ammonia, the real challenge is related with how to produce or from where we can get the hydrogen. This is like the main challenge. And here I am sharing with you as I told you before, that we are producing more than 100 million tons per year of hydrogen. We're still speaking about gray hydrogen. And if you see the methods of production, we have 4% is coming from oil reforming, 22% from coal gasification, 72% from steam methane reforming, and as you can see, just 2% is coming from electrolysis, that means green process. So if you can see here, that means we still rely on fossil fuels to produce hydrogen. That we call it brown, gray, we see that later. That means 98% of the worldwide production is coming from fossil fuel basis. And the steam methane reforming, that is taking 72% of these parts. Why? Because it's considered among the other technologies the cleanest one, because we are producing less CO2 or greenhouse gases compared to the coal gasification oil reforming. That is the most cost-effective one nowadays, and also using natural gas to produce hydrogen. Natural gas is used as feedstock, is easy to handle at industrial level. So I will give you just a brief overview how we produce hydrogen from this method, steam methane reforming. You see here that we have two equations, 1 and 2, and at the bottom we have the result of these two equations. To produce hydrogen, first we need to take methane, that is CH4, mixed with water, and we need to have the right catalytic conditions and also the right temperature and pressure. You see here that the first reaction, we call it the steam reaction, that is occurring between 750 and 1000 degrees, it depends on the type of the catalyst that we are using. And the pressure between 20 to 35 atmosphere, we need to have the right catalyst. And at that moment, we are able to produce 3 molecules of hydrogen. But of course, in parallel, we are producing monoxide of the carbon that is dangerous. So we cannot stop the reaction here. This is the reason why we are taking this CO2, mixing it again with other molecule of the water in other reactor with different conditions of the reaction. At that moment, at this second reaction, we are speaking about temperature between 200 to 400 degrees C, is lower than the previous one, and pressure also is lower than the other one, and we are using other type of catalyst. And the CO, monoxide of the carbon, is mixed with, water to form CO2 and hydrogen. This second reaction, we call it shift reaction. That means from the first reaction and second one, we have the general reaction that we call steam methane reforming. With 1 molecule of methane, 2 molecules of water, we are able to produce 4 molecules of hydrogen and 1 molecule of CO2. The question here, for each 1 kilogram of hydrogen that we produce, we are producing in parallel 9 to 12 kilograms of CO2. This is a huge amount of CO2 that we are producing. And just to give you an idea that we are speaking about steam methane reforming that is taking 72% of the methods of the production of hydrogen, we are throwing to the atmosphere between 650 to 864 million tons of CO2 each year. This is the reason why we should think about clean process, green process that will allow us to decrease these greenhouse gases that we are throwing to the atmosphere. And from there coming the idea of producing hydrogen in green process, in green way, to cut with this emission of CO2 and greenhouse gases. And this is possible thanks to many methods that we are going to see later. And I guess now you get idea clear about how we are producing hydrogen nowadays, gray hydrogen, what is the problem, and why we should shift to other methods to produce hydrogen in green process. And I guess through my presentation, you hear many words. You hear waste hydrogen or gold hydrogen. That is the hydrogen that we can find underground. We hear about gray hydrogen is the hydrogen produced from C-methane reforming process. The brown hydrogen is the one that is produced from coal gasification. Blue hydrogen, in case that we are able to cap the CO2 that we are producing during the production of gray hydrogen, and at that moment we are giving a classification as blue hydrogen. We have turquoise hydrogen that we do a pyrolysis of the steam, of the methane. That means from the molecule of the methane CH4, we are going to get hydrogen plus carbon, hard carbon, not CO2. This is, we call it turquoise. And pink hydrogen, if we use electrolysis powered by the electricity coming from nuclear, we call it pink. But pink and green, we have similar process for the electrolysis that we are going to see later. Just the difference is the source of the electricity that we are using in the process. If it's coming from nuclear, we call it pink. If it's coming from hydrogen, from renewable energy, we call it green hydrogen. But at certain point, we should cut with this kind of classification of colors because it's a big mess from where each one is using its classification. And we should just discuss about the greenhouse gas footprint for each technology. That means how many molecules of CO2 that we are producing when we are producing 1 kilogram of hydrogen. And this is the international, is going to be like adopted in the international hydrogen classification in the future, not yet adopted yet. For the production of the green hydrogen, okay, also we have many methods that can be used to obtain green hydrogen, green molecule. We have what we call biomass process. That means we are using biomass via different two technologies. Biological, that means we are using some enzymes to break the bonds and to produce hydrogen, or thermochemical, that means firing the biomass and to produce hydrogen. And we have the second approach by water splitting. That means, as you see, hydrogen is getting his name because he's making part of the molecule of the hydrogen. Each molecule of the hydrogen is having 2 atoms of hydrogen, 1 atom of oxygen. That means if we are able to break this atom of water to oxygen and hydrogen, it will be a good way to have the hydrogen in clean process. And of course, also with this kind of water splitting, we can have different kind of process. Photolysis, that means we are using semiconductors, like similar ones that we are using in photovoltaic. Just by the light, we can be able to break the molecule of the water, so oxygen and hydrogen. Thermolysis, where we are using just thermally driving process. That means we provide heat to break the molecule of the water to oxygen and hydrogen. And electrolysis, where we are using electricity, mainly electricity can be combined as well with thermal, but mainly electricity to break the molecule of the water. That means even that with this process, you see that we have different methods. What means water electrolysis? That means just having the molecule of the water with 2 electrodes that you can see in the photo there. We have the anode and the cathode. We provide electricity and we are able to start forming gases, one at the cathode and one at the anode. Of course, the one in the cathode is hydrogen, the one in the anode is oxygen. That means we should just have source of electricity and we can break the molecule of the water. The history of this technology is not like something like new, it's very old technology that in the year 1789, these the 2% or researcher Damien and Troswick, they tried to use an electrostatic generator to discharge the current of the electricity in water. And they used 2 electrodes of of gold to discharge the electricity. But when they start the experiment, they observe that there are some gases are forming, and at that moment, they didn't be able to identify these gases. And later on, when Alessandro Volta, he developed the photovoltaic pile, they discovered that normally at that moment that these gases are hydrogen and oxygen. And from there was starting like in 1834 that Faraday established the fundamental laws of electrolysis. That means it's very old technology. And when we come to the 1902, we have more than 400 industrial water electrolysis in operation. That means at the beginning, we were producing hydrogen via electrolysis, but with the discovery of the oil and petroleum at that moment, the other technologies are cheaper compared to the electrolysis, where we need lots of electricity. The other technologies becoming more dominant for the production of the hydrogen. And when we speak about electrolyzer technologies, also we have different kind of methods. We have what we call alkaline water electrolysis, anion exchange membrane electrolysis, proton exchange membrane electrolysis, and we have solid oxide electrolysis cell. That means we have also different approach methodologies. How to do the cracking of the molecule of the water is depending of the electrodes that we are going to use, the solution that we are going to use, and so on. And here, just to give you an idea, we are not going to enter deep in discussion about these technologies, but you can see in the when we see the reaction, the full reaction of the water cracking, that you can see at the top that we have the molecule of the water that is breaking to hydrogen and oxygen gases when we have a source of electricity. But the equation that when we go on details, depending on the technologies, we can have different kind of mechanisms. As you can see in the half reaction that we are occurring at the cathode side, anode sides at the bottom. When we are speaking about alkaline technologies, that we have a Kawash solution. That means this is a basic media. We have the first reaction starting from the cathode side. The electrons is going to there to react with the water, and we have the formation of the hydroxide plus hydrogen at the cathode side. Of course, this hydroxide is moving from the cathode side. You can see here the hydroxide moving from one side to the other side, and there where we have the second reaction that is producing water, and of course we have the production of oxygen at the other side. In the case of the PEM technology, the process is completely different. You see that at the anode, at the cathode, the anode that normally we are producing protons and oxygen, and after that, this proton instead of hydroxide, we have a proton that should move from the anode side to the cathode side, and there we have the formation of the hydrogen. In the solid oxide cell is completely different. There we have the cathodes are based off nickel or yttrium stabilized zirconia, and there we have like the reaction is starting from the anode side to form the cathode side to form the anions of the oxygen. And of course, we need to have an electrolyte that will allow us to have the transport of these anions from the cathode side to the anode side, and there we have the formation of the oxygen. You see that the mechanisms are different. The PEM is, we are using just pure water, and we have a very, very acidic media there. As you can see that we are forming hydrogen. This is the reason why in this technology we need to use some metals that can resist to this acidic media, and we are obliged to use there the platinum or rhodium, that is noble metals in this cathode, which is increasing the cost of this technology. But in the case of the alkaline technology, we are using cheaper electrodes based on nickel and cobalt and iron. There's like the difference between these two technologies. But you can see here, just to give you an overview, that when we are using different technologies, the mechanisms behind them are completely different. Just to share with you these photos, this is the large-scale alkaline water electrolysis that was operating from 1928 to 1971, and with a capacity of 165 megawatts was installed there, this one in Norway. And as there they have hydropower, electricity coming from hydropower. It was, from commercial point of view, very attractive to produce hydrogen in this way from 1928 to 1971. Then this the installation from how was in this period. Later on, this other installation that we were having also in Norway with a capacity of 125 megawatts is atmospheric pressure alkaline water electrolysis that also was operating up to the years 1991. We have the other one even in Africa, in Zimbabwe, in Kwikwi, that an installation was operating from 1972 to 2015 to produce hydrogen. That means here, if the electricity that we are using to produce electricity via this technology coming from renewable energy, we can call this kind of molecule or this hydrogen that we are producing a green hydrogen. If just not to enter in lots of details, but in both technology or in all technologies of the electrolysis, we have all the time anode, cathode, and electrolyte. For alkaline technology, at the anode we have oxygen evolution reaction, and we have there the base material is nickel. Catalyst, we are using nickel or nickel iron or nickel cobalt. It depends of each company that they are developing their own IP that they are going to use. But of course, when we change the nature of the electrode, we are changing the efficiency and so on. That means, and also the lifetime and so on. But in any case, we have different technologies based on cheaper material compared to the technology of PEM. And in the case of the cathode, we call hydrogen evolution reaction, HOR. That's also, we have the base material is nickel, and the catalysts are also pure nickel or activated nickel. And we have some advanced catalysts that nowadays in the market is based doped by metal, by molybdenum or by aluminum or by cobalt and molybdenum. That means we have different technology in the market aiming to increase the efficiency, decrease cost, and increase the lifetime. This is the main purpose of these developments. And for the electrolytes, at the beginning of this technology, they were using asbestos, but as asbestos is considered a cancerogen for a human due to these health concerns, this industry, they moved to other kind of electrolyte that's called it Zircon, that they are using to separate between the cathode and anode, and of course to allow to the hydroxide to move from one side to the other side. And they were using like 500 micrometer thickness of this kind of electrolyte separator. But nowadays we have other technology that in order to have a compact system, moving to other thinner layer of this kind of material to arrive to less than 300 micrometers. For the PEM technology, as I explained before, that normally for oxygen evolution reaction or hydrogen evolution reaction, we have the proton. Proton, that means we have acidic solution. That means we need to have metals that can resist to the corrosion of these harsh conditions. And in this case, in the anode, we are using iridium-based coated on tin core. That means we are using noble metals. And for the cathode, we are using platinum or platinum palladium or platinum rhodium as a electrocatalyst in the cathode side. And for the membrane that we are using, that should have a clear separation between cathode and anode to avoid that we have cross diffusion of the oxygen and hydrogen that we are producing. If not, we will have an explosion. We are using Nafion but should also allow the transport of the proton. That means hydrogen can move from one side to the other side. And in this kind of technology, we are using the Nafion, is the unique one that's used now in the technology of PEM. Of course, there are other developments ongoing, but is the unique one that is used in all technologies as a membrane in the technology of PEM. The third point also to discuss, because when we are speaking about cracking of the molecule of the water, we need to have energy, and this energy we need to optimize it to increase the efficiency of the system. But from the cell potential that you see on the right side, you see that the voltage, the electricity or the potential that we need to break the molecule of the water is depending on temperature. Of course, when we increase temperature, we are decreasing the cell potential. And to break the molecule of the water, we need the energy just to break the bonds. This is what we call the energy that is responsible of the water splitting to break the bonds. And of course, we have other parameters because this reaction is endothermic. If we just demonstrate the sufficient energy, what we are going to have is the temperature of the cell will decrease, and of course we are not be able to break anymore the reaction, the molecule of the water. This is the reason why we should supply an extra to control the temperature of the cell, and we have something related with the efficiency of the element that we are using. As I explained before, for each cathode, anode, we have different kind of metals that we are using, and of course each one is having like some kind of limitation regarding the electrical resistance or regarding the formation of the bubble clouds and so on. That means we have many parameters are interfering to have the energy that normally we need for each kind of technology to break the molecule of the water. But in general, if we have a complete, efficient system, 100%, we need just to have 39 kilowatt hour to produce 1 kilogram of hydrogen. But of course, at the real case is we are not able to achieve that because this is like the ideal, but we are close. Normally, we are speaking about 50 kilowatts per each kilogram of hydrogen that we are producing. And of course, to calculate the efficiency of the systems that we are finding in the market and that we are using to produce hydrogen, of course, we need to calculate via this equation what is the heating hydrogen value of hydrogen that we produce and divide by the electricity that we use to produce it initially. That means here we can have the efficiency of this kind of technologies that we have in the market. Sorry. Also, another important point is the footprint of this technology. As you see, the POM is more compact. You see that the picture on the left side, there's electrolyzer of capacity of 3 megawatts electric. You see the person that is close to him, just to give you an idea about the scale. But in the case of alkaline electrolyzer is bigger. And you can see that the footprint is almost 2.5 times bigger if we are using alkaline technology and POM. But it's not critical. It depends on where we are going to have this kind of facilities. For example, we know that Morocco is going to make this installation in the southern region of Morocco, that where the footprint is not critical. But for other kind of industrial application, also we should consider POM for footprint impacts. But of course, also there are some kind of differences about the operation of these two systems. It's not like both of them are adapted to work under all kinds of conditions, but there are differences between them. Here, just to give you a summary, alkaline POM technology, I will not go through all the elements that I was discussing before about the charge carrier, temperature, and so on, pressure, and so on, but it's a question of the system response. You see there that, for example, alkaline technology is having a system response in question of seconds, other one of milliseconds. What that means? That means when we are trying to use renewable electricity to produce hydrogen, we have the question of intermittency. The POM technology is more adapted to work under intermittency, but of course the cost is high of this technology. That means we should look for the good ratio between both technologies, that alkaline technology can work under a static mode or constant mode of the electricity profile. And for the part where we have the intermittency, we should implement the POM technology that is more adapted and less critical for this technology, the change of the profile of the electricity. When we come to the maturity, we can consider both of them are commercial, but if we are speaking about maturity, alkaline is more mature. POM, we still need to do a lot of effort to decrease costs or to increase efficiencies. And we have as well other technologies like UM6P, just to give you an overview, but we are not going to enter in details because this laboratory is still at early stage of commercialization. Nowadays, we are coming to the summary, just for this part. In ammonia, we discussed from the beginning about ammonia as important molecule for fertilizer for many industrial application. You can imagine if we have good solar, and we have seawater, that means we can produce ammonia. That means we need just to have a water purification unit to produce pure water. After that, the electrolysis to produce hydrogen. We can produce, and also we produce nitrogen from the air. At the end, we can get the ammonia that can be used in different applications like food feedstock for many industrial process or as fuel or as fertilizer. The other application that we can use ammonia is to decarbonize the maritime transport. Is also a very important because it's hard to decarbonize via other kind of solution, but can also be a solution to decarbonize the maritime transport. And why ammonia? Because when we are burning ammonia or using a fuel cell to produce electricity from ammonia, we are not emitting any CO2. Ammonia is having the advantage that's higher energy storage density compared to the hydrogen. And also we have already existing global infrastructure like ports and transport. And how it works, that ammonia can be fired or can be cracked. That means we can use thermal engines to produce the power that need to drive the ship, or we can use fuel cells. Later on, I'm going to give you an introduction about what means fuel cell. And also can be used completely as fuel or can be also mixed, blended with other fuel that we are using in the ships. And of course, if we use green ammonia, that means we are not emitting any greenhouse gas to the atmosphere, and the whole process is green, and we can be able to decarbonize the maritime transport. I mentioned before the fuel cells, because when we have hydrogen or ammonia as fuel, we can use a burner like in classical thermal engines to burn them, to produce heat, and from heat we can have a mechanical energy, but also there are other ways that is more efficient, how to use hydrogen or ammonia, and also to cut with some kind of difficulties that we can find or some kind of problem is the fuel cell. What means fuel cell? Fuel cell is the inverse of the electrolyzer. That means when we use the electrolyzer, we are able to break the molecule of the water to oxygen and hydrogen and to produce electricity. But to produce hydrogen, we can produce hydrogen, but we need electricity. In this kind of, for the fuel cell is the inverse. That means we need to have the feedstock hydrogen from one side, the anode side. We have the oxygen from the cathode side. We associate them via the electrolysis, electrocatalysis that we have between them, and we are able to produce steam and electricity. And here, just to show you an example of application of fuel cell in mobility. For example, this is a car that you can see here that we have the reservoir in the bottom. You will fill it by hydrogen in the reservoir you have here. And there you have the fuel cell, this fuel cell that we are injecting hydrogen from the reservoir and the air coming from the atmosphere, and we are able to produce steam that can come outside. That means the unique co-product that we are producing here is just steam, and we have the electricity that can be used in the electrical engine to drive the car. Of course, we have many cars are running worldwide by hydrogen, like Hyundai Mirai. We have others that are already commercialized one. But of course, the cost is higher compared to the batteries. But of course, this technology can be used in other sectors that we cannot imagine to have batteries, like maritime, I was showing to you before, or the heavy duties like trucks. That's we cannot imagine to use batteries there because we need a lot of power, and also the battery will occupy a big part of the truck. And hydrogen, for example, these are commercialized heavy truck by that's called high-tech hydrogen system. And as you can see here, we have the reservoirs of the hydrogen, and we have the fuel cell with a power of 180 kilowatts, is a combination of two fuel cells, and with a battery to have like the storage of the electricity that is producing during the reaction between hydrogen and oxygen to produce electricity. And after that, we have the electrical engine for the truck. And as you can see, the main advantage of this kind of technology compared to the batteries, if we are comparing two systems, is question of the autonomy. Here we are speaking about 724 kilometers under optimal conditions. And the refueling time, because battery, as you know, we have difficulties how to charge, even that if you can imagine for heavy truck, how the size of the battery is going to be, and the time to spend to charge this battery. But in this case, refueling time, it will be shorter. It's like refueling the oil or the diesel now in the stations. This is the main advantage. And of course, we have all kinds of transports used worldwide that we can have a version of hydrogen, like the railway between, this one is operating between Germany and France. We have helicopters, we have mining truck, industrial vehicles. We can have the application of the fuel cells in all kinds of transport that we can have. But of course, we should look for the economics. We should look for the business. If really there are a competition with other kind of technology that is already in the market. For example, for cars, we know that the batteries are doing the same purpose to decarbonize the mobility, but of course cheaper than hydrogen car. But in other kind of scenarios, we cannot imagine to have just 100% electrical cars with batteries, but we need to introduce hydrogen in the mobility. Now we arrive to the part that is very important about the challenges and opportunities. Of course, as any kind of new emerging field, what we find like we have lots of difficulties, lots of challenges, but of course from these challenges we can find opportunities. For the hydrogen, we have the cost gap, because when we speak about green hydrogen, it's more expensive than gray hydrogen. We are speaking about the water scarcity that we have in many countries. We have the transport of the hydrogen, training of the skilled people, development and research, and we have other kind of difficulties that we should deal with them. But from these challenges, we can find many opportunities. For example, costs. We are speaking during this presentation about the methods of the production, but if just we want to compare in a rough way, we are speaking that now the methods of the production of green hydrogen, as you can see here in the green part, is more expensive than the methods of producing hydrogen from fossil fuels. Is almost 2 times, 3 times. And of course, there are a bright future that we can have to decrease the cost in the future by the reduction of the cost of the electrolyzer. Of course, when we upscale the production of the electrolyzers, that by consequence we can decrease the cost. We have also the question of the electricity cost. When we are using renewable electricity, that means we can decrease the cost even more and more with the time to have a very competitive cost, very competitive price that can allow us to decrease the cost of the production of hydrogen. We have the efficiency, that also we have a lot of research work to do to increase the efficiency of the technology that we have nowadays in the market, and also the question of the quality of the electricity that we can have to allow us to have full load hours, to increase them, for example, or to operate the electrolyzer for more time during the year. And we have also the question of the lifetime. If we are able to do effort in all these parts of the development, for sure, at a certain point, we are going to arrive to a price of green hydrogen can be cheaper than compared to the other technologies that they are producing hydrogen from fossil fuels. That means the future, if we are speaking, that hydrogen, green hydrogen, can be a very competitive. And this is a study that was developed by DOE and also International Energy Agency and the ARENA. The second point about electricity demand, why we are speaking about Morocco? Because when we are speaking about the production of hydrogen via electrolysis, that means we are not speaking just to have the cost of electricity very low, but also the quality of the electricity. When we are using just electricity from one renewable source like sun, we can operate our electrolyzer during just the day. That means the full load I was discussing in the previous slide, we are going to have a shorter time of the production of the hydrogen during the day and during the year. That means we need to have the quality. This is the reason why we should have an energetic mix. That means we should use different kind of source of renewable energy that are complementary between them. There is a complementarity between them, like wind energy and solar power. And if you see in the southern region of Morocco, of course, in all these parts, we have a good quality of the wind and we have good quality of the solar. That means if we are using both of them, we are going to operate our system for more time during the day, not just during the sunny hours, but also during the night. And this is not the case for Morocco. We have many regions in Africa where we have solar with wind, good complementarity between both of them, or we have also geothermal as source of renewable energy, or we can have also maritime energy as well as a mix that we can use for the energy mix. That means Morocco is very attractive from investment point of view because we have this energy mix. The second question when we are speaking about water demand, the person that they are speaking just, okay, I am using the energy to crack the molecule of the water, that means I am consuming more water, but this is not the case because if we compare the other methods of steam methane reforming, as I told you before, in the reaction we are using the molecule of the water to be combined with the methane to produce hydrogen, we are using more quantity of the water in all the value chain, in all the process. In the case of the electrolysis, we are using less molecules of water, 8 to 10 kilograms to produce 1 kilogram of hydrogen. But as you can see in the case of steam methane reforming, we are between 13 and 18, is almost a double. Or in the case of coal gasification, we are using a lot of quantity of the water to produce 1 molecule of the water. And also the person that they are scared about the future, if the water, okay, will be consumed here. If we speak nowadays in 2022 that we have 90 million tons of the hydrogen that is produced, and we do the expectation according to the growing that this field can have, in 2050 we'll need 500 million tons of hydrogen. This 500 million tons, what is the quantity of the water that we need to produce it is around 25 billion cubic meter. And if we compare it with the actual situation, it's very small compared to the water that is used in agriculture, in industry, or also in municipal, and is equivalent to what we are producing nowadays worldwide from the seawater. That means the quantity here is not huge, but in the contrary, if we are developing green hydrogen field, of course, that we are going to implement the solution for desalination, and this can help us to decrease the cost of desalination, but also to have a social impact on the communities that nearby to provide them drinkable water. And when we come from the economical point of view or the energies we are consuming here, as you can see, that for each cubic meter of desalinated water via reverse osmosis, we need 3 to 4 kilowatts. When we come to the economies, that means the contribution of the cost of the salination unit is between $0.01 to $0.02 per kilogram of produced hydrogen. That means is almost negligible, and we should not be scared about using the salination unit to produce green hydrogen. That means here the offtakes that hydrogen will promote to have cheaper desalination technology and clean water access to nearby communities, and this is also very important. The other challenge, how to transport hydrogen. It is like also a big question because we cannot use the current infrastructure that we are using to transport natural gas, to transport hydrogen. Of course, there are many studies that we can use it in blended way. That means we mix hydrogen with methane, we transport it to other place, and there we should separate the hydrogen from the methane. This is a way how to use the infrastructure that we have nowadays. But of course, hydrogen can be used, can be transported via ammonia. That means, what means that? That when we produce hydrogen here in Morocco, we convert it to ammonia. Ammonia is going to be transported to other countries that can be used as ammonia. Or if they want to use it to have hydrogen, we have the cracking system to break the molecule of ammonia to hydrogen and nitrogen. This means the infrastructure that we have nowadays worldwide can be used to transport hydrogen via ammonia. And as you can see in this map, here we have the loading and unloading facilities worldwide of ammonia. You see here in Morocco, we have 2 red dots. Why? Because we are importing ammonia. As I explained before, UM6P is importing 2 million tons of ammonia per day. You can imagine that tomorrow, if we are producing green hydrogen, green ammonia in Morocco, these 2 red dots can be converted to blue dot. That means we can export ammonia in the future. And this is also giving us a great opportunity in Morocco to promote the production of green molecules in Morocco. Second point is about this mid and long term that you know and you heard in the news that Morocco wants to develop this gas pipeline from Nigeria to Morocco, and also is going to go to Europe, going through 19 countries. And according to ONIM, that they declared that this pipeline will support the transport of hydrogen in a blended way. And of course, in the future, we need to have new infrastructures that can support the transport of hydrogen at 100%. That means Morocco is having a very strategic location. And also we have existing transport infrastructure. That means we have ports, we have ships, we have everything that can allow us to promote the export of green ammonia worldwide. The third part is related with the research, development, and innovation. Of course, when we are speaking about green hydrogen, green molecule, we are speaking about all the value chain from the feedstock. That means we need to have renewable energy. We need to have green water. That means desalination of seawater. CO2 capture. This is also a great field to produce e-fuels in general. We have the production. What are the methods that we are using currently, and how we can develop them, and how we can develop emerging technology that can be better in the future. The conversion, that means when we're speaking about green ammonia or green methanol or e-fuels, we need to develop technologies that can decrease costs or increase efficiencies. Handling of the hydrogen and the green molecule, that means the storage and transport. We have the question of conversion, how we get use of this molecule that we already produced. That means we are speaking about thermal combustion engines or fuel cells that I explained to you before. And the final application, a part of the fertilizer, that is, we are mastering that in Morocco, but we look for other kind of application like iron and steel, the direct reduction of industry, I guess. To use hydrogen to reduce the iron mineral to iron metal via hydrogen reduction reaction. For that, here at the university or in Morocco, we are driving a very promising research and innovation portfolio. And if we are speaking about short term, what is urgent to do, for example, in the field of renewable energy, even that these technologies are already mature and commercial, and we are using them in Morocco, but also we need to look how to have a good hybridization between solar and wind, using AI to forecast as well and to predict how is going to be the behavior of the profile with the time. We have the question of the alkaline technology. We have many developments are going on at the university. For example, zero gap alkaline to decrease cost, or low noble metal for PM technology. That means also this one, the aim or the target is to decrease the cost by the double or even 3 times to arrive to a competitive cost of $300 per kilowatt. We have the case of conversion, improved Haber-Bosch catalyst. That means a system that can operate at lower pressure and temperature. In the case of ammonia transport handling, the question of cracking of ammonia, we have lots of research to do there to develop an efficient system. And reconversion, there we have the durability of the fuel cells that also should be targeted here for maritime or for heavy trucks. And for the utilization, the hydrogen-based direct reduction iron, that means we can use in industry here in Morocco. And we have as well the midterm that we should look for emerging technologies, because the technologies that we are using nowadays maybe can not be used tomorrow due to cost or due to the limitation of the technology. That means we should look for the future. For example, just giving you here some examples for feedstock, how to capture the advanced direct air capture. That means to capture CO2 from the air that can be used to synthesize methanol or e-fuels or ethanol and so on with hydrogen. For the production of the hydrogen, we have SOIC, is very promising technology that can be used with higher efficiency and also can be used to have heat integration, where we have industries that they have waste heat. That means these units can be more adapted to produce hydrogen. We have, in the case of conversion, to have direct electrochemical ammonia synthesis instead of going via producing hydrogen via electrolysis and then Haber-Bosch. That means we can have just one system that can allow to have direct electrochemical ammonia synthesis. In the case of handling of the hydrogen, we have the solid-state hydrogen storage that can be safe and with higher density. And of course, the main drawback of this technology is the temperature of dissociation of the hydrogen. That means we should look for solutions where we can decrease temperature. For reconversion, we have to develop advanced combustion for ammonia in engines, because when we are burning ammonia, we have the question of formation of NOx gas. That means how to develop catalytic catalytic combustion reaction with lower NOx gases. And also utilization, we have many kinds of utilization of hydrogen or green molecules in industry. That means we have a very rich portfolio that we should perform to meet the target of the implementation of green hydrogen, green ammonia in Morocco in short term and also in mid-term. For the training of the skills, also at UM6P, we are working to have a diversified portfolio of training programs, initial or executive programs, and also doctorate program. We have lots of PhD students that they are performing their PhD in this emerging field of green hydrogen, green molecules. But of course, we have also our bachelor programs, and a part of that, we have like what we call executive program. I will give you just one example of our executive program that we ran in 2023-2024. The first edition, we are having with us 54 participants that are now the leaders developing this field of green hydrogen in Morocco. This year, in this edition of 2025-2026, we have even participation not just from Morocco, but also from Africa, from Tunisia, from Mauritania. That means we are impacting as well Africa to prepare the right skills. But of course, we are having a very rich portfolio that we are going to present depend of the industrial need. That means from the engineering point of view, or also from the operation point of view, we can answer to all requests, as we have a very complete platforms at the university that allowing the persons not to do a theoretical courses, but also to apply the concept of learning by doing. That means to get in the lab and to go deep in understanding how these new technologies are working and what are the main purpose to consider when you are operating them. As conclusion, this was a discussion of the panelists, the experts that were here today during the lunch, how to move from vulnerable fossil fuel supply. That means what we have nowadays is what we have in this part. As you see with any kind of crisis, like the crisis that we have nowadays of the Strait of Hormuz, we have a big inflation. That means the cost of the life, the cost of the energy, the cost of chemicals, the cost of the food is increasing. We can move to other scenario that we have sovereign green economy. That means it's not just question of having sovereign energy supply via green hydrogen. We can have all kinds of molecules that can be used in combustion or also in fuel cells to provide energy that we need. We have the question of the sovereignty of having chemicals, because as you know, from hydrogen, CO2, we can produce all kinds of fuels that we are using nowadays, and we can have as well green ammonia that we are using as fertilizer. That means it's possible to move to have this green scenario. That means moving from fossil fuel-based system to green economy based on the development of green molecules. But of course, we have the question of, first, that we are speaking about economics, about what is the cost. But of course, there is also a decision that should be made to go through this kind of implementation. And as you can see, that we have a successful story in Morocco about the management of the water. That means in the past we construct mini dams, and nowadays, hopefully, with this good year, we have a good reserve of the water. Other countries are suffering from the scarcity of the water, but for us, we have now a water that can serve for the next 3 years And also we have the good management of the renewable energy. As you see that in Morocco, we have a big integration of renewable energy in the electricity system. We have the complex of Ouarzazate. We have the installation of renewable energy everywhere in Morocco. And this is also a good example. And I believe, as professor here, that the future will be bright for green molecules in general in Morocco. With that, I will finish my presentation, and thank you for your attention.
Thank you so much, Professor Faik, for the presentation. It was an in-depth presentation taking us from the basics to covering the different use cases and the challenges and potential solutions. So for the best of interest of time, we have a Q&A, but we'll take 2 or 3 questions. Do we have any questions from the audience to start with? We have mics around, so if you have any question, please just raise your hand. Okay, so maybe I'll start with a question that I have. You have mentioned many sectors, industries. So beyond the current uses that we see of the green hydrogen, which sectors or industries do you believe in Morocco specifically will be using green hydrogen at scale first? And of course, why is that?
First sector, this is clear, is in the domain of the fertilizer. This is the reason behind the big investments of the group UM6P to implement the production of green ammonia nowadays in Morocco, because as I explained before, nowadays they are importing more than 2 million tons of gray ammonia, not green ammonia coming from methane. If we are able to arrive it, to develop it in Morocco, of course, the first application usage of green hydrogen field is going to be green ammonia for fertilizer application. We have other sector also is very important, is for direct reduction of iron. This can be used in steel industry. And of course, there the equation is very simple, because you can have a unit for the production of green hydrogen can be integrated directly to the process and to have this green process without the emission of greenhouse gas. These are the 2 main applications that nowadays we can speak about them. But of course, the other application is depend of who is going to be the off-taker, who is going to be the difference of the cost of the production of this molecule, not using the gray molecules. And also it's going to depend on the regulation. This is why we have today with us Professor Heino von Meyer. He will speak about geopolitics, just to understand, okay, we have a cost gap, who is going to pay, and how geopolitics can promote this kind of developments. But apart of that, I think in Morocco we have a great opportunity now to implement this kind of technology that as we have a real need from our industry to apply this kind of molecules.
Yes, maybe just one question from my side. Since we are in a scientific context, how can Morocco leverage its scientific ecosystem to create this sovereignty that we're speaking about?
Yeah, for this system, we have now a very, very rich ecosystem, because if we are speaking about from the research point of view, we are speaking before to come to industrial implementation. We have what we call technology readiness level, that's going from scale from 1 to 9. That means in the laboratories, we have different entities in the at the university that they are from different perspectives trying to find solution for the current technologies, or also to develop emerging new technologies related with this field. That means we are speaking about development of applied research or laboratory scale. After that, we have also a system that's trying to accelerate this kind of development that we have at the university to other level technological development, like Innovate for Industry. We have Green H2A, we have ICX, we have many entities that they are working as well to move this kind of development to other level. And of course, we have Innovix, we have Hydrogel that are present with us, that they are looking for to create, to transform this kind of opportunity to a real industrial opportunity. And we have UM6P that is behind that to promote, because at the end, as I explained from the beginning, as we have the cost gap, we should have off-taker that will guarantee that this kind of development will find place at industrial level. That means we have a very rich ecosystem that is helping to promote this green technology, green hydrogen in Morocco. just in my opinion, we need to accelerate more.
Thank you so much, Professor. And luckily, we have all these players with us in the room, so we will have the opportunity to tackle these in details more later. So we see a question in the back. Do we have them? Can we hand them the mic?
Thank you so much, Professor, for the insightful presentation. I just wanted to find out if we still have a huge potential of using green hydrogen in cement industries, like during the production of cement, because it's one of those that usually produces a lot of carbon dioxide during the heating. Do you see the potential of using green hydrogen in that field?
Yeah, just to tell you that hydrogen can answer to all kind of industrial demand regarding the heat. That means as I explained before, that is having a high gravimetric energy density, and you can have heat that can be adapted for all kind of temperature. What we should make attention here when we are burning hydrogen, because for other kind of applications, we are using fuel cells to produce electricity from hydrogen. But when we are burning hydrogen or green ammonia at high temperature, we are not forming any kind of CO2 gases. But the question that at high temperature, as we are using air instead of pure oxygen, we have the side reaction that's where we are forming NOx gas. That means during burning, we should just to control via catalyst or via other kind of technologies to not form these NOx gases that are responsible of the throw of the ozone in the past. That means this is like the unique limitation that I can see. But of course, burning hydrogen or burning other kind of or ammonia, we can have heat that can answer all industrial needs, among them the cement industry.
Thank you so much.
Yes, we do have a question here at the front.
Thank you, Tiab Samad, for your very comprehensive presentation. So I'm not aligned with your statement that the priority will be to use ammonia for fertilizer production, because as you said, at least for the short term, the cost of ammonia, of green ammonia, will be significantly higher than the gray ammonia, and fertilizer are directly used for food production, and this will have a direct impact on the food production. And therefore, I don't think that this will be the priority worldwide, because maybe some areas like Europe will have regulation in order to have, to favorize the green fertilizer, but elsewhere in the world, they will not be willing to pay this additional cost.
Yeah, I agree with you. This is the reason why today, and also during the panel of discussion, we will discuss this question of this kind of question, because we have a cost gap. This is clear. Who is going to pay that? Just an industry that wants to decarbonize their process, and they will pay this kind of cost, or it depends on geopolitics. If we have some kind of rules worldwide, to have a niche for green fertilizer at that moment, if we have the client that can pay this difference to have green fertilizer instead of the fertilizer that we have in the market today, is a very complex question, but just allow me to give you an example. If we come to the question of development of electrical cars, China, they start to work 30 years ago. They were assuming the cost gap, and now they are dominating the market. Even the Europe are 50 years behind them. If we are speaking nowadays, just in this week, China, they announced, okay, they are going to develop hydrogen car. No one is thinking about that. Maybe in 20 years, Europe and us will told that, okay, we are too late. For me, Covering this cost gap should be made in somehow. But to promote this technology in the market, for me, it should be a must. Order coming from top, we should accelerate this development.
I'm fully aligned with this statement. We have to prepare ourselves, but what I think is that for the short term, fertilizer will not be the priority. But it is clear that if we develop the technology before the others, we are on the right track. Thank you.
You're welcome.
Thank you. I think we have one last question that we can take.
Thank you, Professor Absamar, for this nice and clear presentation. I have a question here regarding what is the main challenges limiting the widespread adoption of hydrogen. We are seeing that high production cost, and also we have a problem of storage. The same, for example, we can check the case of renewable energy in the beginning. When we discussed with wind turbine, solar panel, not adopted. Now we're discussing about storage, batteries, etc. And the same case for hydrogen. I think its main challenge is also to adopt or to use hydrogen today.
Yeah, I agree with you. There are lots of challenges. This also, when I mentioned the challenges, among them is the storage transport. We are speaking about hydrogen because, as you know, if we have the hydrogen molecule, to store it, we need to increase the energy storage. We need to go to high pressure, like 350 bars or 700 bars, which increasing the cost of the storage. If we want to go to liquid state, we need to go to minus 256 degrees C. Is difficult to manage. This is the reason why we are considering, okay, the hydrogen should be produced depend of the need, because you can just imagine we have gas stations. Instead of suministrating hydrogen there, we can have the localized electrolyzer there, powered by renewable energy, to produce the hydrogen that will be used in the day and to be consumed. And this is also why we are discussing also in the before about the question of using other molecules to store hydrogen, like ammonia. If you use ammonia or you use other molecule, can be used as other way to store hydrogen. But of course, hydrogen of storage can be used just for final application, like in mobility, like the things that you are doing. You need to have a reservoir in your car, or for small unit for the storage of the hydrogen. When we move to have a bigger capacity of the storage, we need to go for other kind of cheaper solution, like underground. But unfortunately, where we are going to implement this solution in the southern region of Morocco, we don't have big reservoir underground. That's where we can store hydrogen. But in other countries like UK or USA, they have big facilities to store hydrogen, not at high pressure, but underground, that is used for industrial purpose. That means these are tricky questions that instead of speaking about the production in massive way of hydrogen in one site, we can have a decentralized way. But in case of the ammonia, the figure is different because we are going to produce it in southern region of Morocco. You have the port there, you have ships, you can transport as much as you want of the ammonia to Jorsfar or worldwide. This other concept. But I agree with you that the question of the storage of hydrogen is a critical question, but at the end it will be depend of the final application where we want to apply this kind of developments.
Okay, thank you so much, Professor.
Thank you so much, Professor Absamad Fayek, and thank you to our audience for your questions and for already engaging in debates and challenging perspectives. So now moving from the lab to the global stage, our next sessions shift the focus to the macro environment and its geopolitics. We will examine the international competition, the emerging Europe, Middle East, Africa corridors, and the regulatory frameworks that will determine the economic viability of green hydrogen. To guide us through these complexities, we are joined by Professor Heino von Meyer. Heino is a senior consultant to the International PTX Hub, a global center of expertise launched at COP25. Head Sustainability and Global Networks at JEZ, German Agency for International Cooperation, with 3 decades of experience at the OECD, including 15 years as head of the OECD Berlin Center. He now focuses on the regulatory and sustainability standards necessary to achieve the climate neutrality through green shipping and the Power-to-X solutions. Professor von Meyer, the floor is yours.
Thank you for this kind introduction. It's a great pleasure to be here, and thank you to Professor Faik for inviting me to hold a keynote in this impressive audience, I must say. It's a great pleasure for me to be back at the campus of UM6P here in Ben Gurion. I had the pleasure 2 years ago to already participate in the Executive Masters series. I hope we can bring up my presentation. Not yet, but I hope soon. Because the green button, that's the secret. So, I will talk about convergence, because the whole week here of the Science Week is about convergence, and I will try to talk about the convergence of the strategic rationales for hydrogen and Power-to-X. And therefore, I will start with the hydrogen hype cycle. Because initially, when the discussions and the politics about hydrogen started, the expectations grew very sharply, very quickly. So there was a kind of exaggerated excitement. But this kind of graphic was actually developed for artificial intelligence, but it fits to the hydrogen cycle too. So there is a peak of what's called inflated expectations around hydrogen, the hype, but you also see the disappointment, expectations going down, and I added, again, exaggerated, because the picture isn't that negative. So in this context, we ask the question, is there really a future, even a bright future for green hydrogen? And I will talk about the global perspective, but Abdesamad Faik already addressed the Moroccan perspective, and I think his answer was clear. Let's see what my answer is. So after this true of disillusionment, usually comes a period of maturity. Yes, some hyped expectations are not fulfilling, but then there comes a kind of slope of enlightenment or plateau of productivity, and you see I've changed from H2 hydrogen to PTX, and several arrows, because it is probably not in the end hydrogen that we need, and we've already heard there are the derivatives of hydrogen, ammonia, methanol, and other options that will in the end really succeed. And PTX probably wasn't hyped that much in the past, but I think it will be the future. Now, when I started and when this hype started, what did it drive? It was very much the climate debate. It was very much about climate change, climate action, decarbonization. Well, we prefer at the PTX hub defossilization. Why? Because we will also need carbon molecules in our industries, but the critical thing is it shouldn't be fossil carbon sources. So climate was the main narrative. But quickly, of course, and Morocco is a typical example, it was not only about climate, it was very much about industry innovation, about industry development. It was about developing markets. So that's the second converging rationale. And now recently, we all read the news and we know that energy security, security of supply, and resilience of our energy system is becoming more and more important. Coming from Germany and the north of Europe, it is clear it is about security. We don't talk about sovereignty because it's clear we will have to import energy in the future from the south. Morocco, I think, rightly can talk about sovereignty because you may reach a point where you are not dependent anymore on fossil or on imports. Currently, you still are, and it will take time, but it's a policy decision if you can go that way. So, convergence of rationales, very nice graphic, which I grabbed from your conference logo. So, climate, defossilization, industry development, security of energy and resilience. And I will now go through these three areas, and I start, with climate again. I guess most people know this graphic. It's not modern art. It's a quite powerful infographic, and you know what it is. It is the increase in temperature over a long period, and you see it's the deviation from the long-term average of the base years 1850 to 1900, and you see that in the first half of the last century, the deviations were around less than 0.5 degrees. And in recent 25 years, the temperatures and the deviation from the long-term average are becoming bigger and bigger. And in 2025, even the 1.5 degree threshold was passed, which is a kind of benchmark which was set at the Paris Agreement. So there is urgency to act. Plus, we know and there is clear evidence that there is a correlation between the warming and the concentration of CO2 or greenhouse gases in the atmosphere. The concentration increased from about 280 to more than 400. So what do we have to do? We have to close the Paris Delta. This shows how over the coming years to 2050, the business as usual trend is, and how we have to decline and break the carbon content and emissions in the global system. And for that, three things are essential. Increase energy efficiency in all sectors should be the first priority. Renewable energy towards 100% wherever possible. Electrification wherever possible. However, you see there is still a dark loophole down there, which we cannot close with electrification directly. That is where we continue to need molecules. And that's where hydrogen and Power-to-X come into play. For those sectors of industry and transport that cannot directly electrify. So how does that work? We've already heard a lot about the chemistry, etc. So I promise I'll try to be quick on this. So we start with renewable electricity, be it wind, solar, create green renewable electricity, and whenever possible, use it directly, for example, for cooling houses, heating houses, for rail, and for cars. Go straight. But there are applications where I said we will need molecules, and here steel factory is one clear example, and that's where you have to combine the green electricity from renewables with water in what was nicely described in an electrolysis process, and you have an issue, where does the water come from? How can you ensure that that's sustainable? And you produce hydrogen, and it's green hydrogen if the energy, electricity comes from renewables. But there are sectors where you cannot use hydrogen directly and where you need a synthesis process. Haber-Bosch was mentioned. That's combining hydrogen with nitrogen, and with that you produce ammonia, for which you have a sector which has already been mentioned many times now, the fertilizer sector, but also explosives, other industries. Plus, you see a ship down there. Ammonia can also be used as a fuel for shipping. The other process is the Fischer-Tropsch synthesis process, which combines green hydrogen with carbon. Now you will say, oh God, we wanted to get rid of carbon. No, for certain products, we need the carbon, but it should not come from fossil sources. Either you take it with direct air capture, or you use biogenic residues, or carbon capture and storage. Important, should not be fossil. And therefore, power to molecules is the story. But there is a danger in the debate that everything is focusing on decarbonization, on carbon, and that we lose the perspective of other important global development challenges, and therefore having a tunnel vision focusing exclusively on carbon emissions can be dangerously misleading. And one way of broadening the perspective is to look at the Sustainable Development Goals, which we have to achieve by 2030, and we are far away. But it's important that we also look at other challenges, such as loss of biodiversity, inequality, and other issues. So don't get trapped by only focusing on carbon. That was part one, I think, on the carbon issue. Now let's move to industry and innovation, and I would like to start with a first message. Many countries initially thought about green hydrogen. Oh, we have wind and sun. We can produce hydrogen. Maybe we have a water issue. And Europe is promising to buy big quantities. So let's go for that. That strategy is dangerous. You can do that, but why not look at how you can use it in your own country? So think about adding value. Think about how you can create growth in jobs and income in your own country by using the hydrogen. And using it for what? I mean, meanwhile, you're here since an hour or a bit more. The first thing that comes to mind, ammonia. You can then export that, but at a better price. But also in the trade and logistics, we already said, you can use it as a maritime fuel. But domestically, you can produce fertilizer. So adding value, increasing the value added and creating jobs, and finally, the fertilizer you use for producing foods. So that's a message I would like to get across. Focus not only on exports, focus on the priorities in your own country, how you can create jobs and value added, and think beyond hydrogen. And this same logic is true for ammonia and fertilizer food, but also for methanol, sustainable aviation fuel, jet fuel, or for sponge iron to green steel. And I will go through quickly, of course, some of these sectors. I don't call it green fertilizer, but rather e-fertilizer. But consider the background. This is the increase in the global population from 1975 to 2050, and you see it almost doubled until now, and there is another 2 billion people expected to live on Earth, and living means feeding them. But the cropland does not increase, at least not significantly. So if you divide the two things, you see that less and less land per person is available. And therefore, using fertilizer and other means of increasing the productivity is crucial. And this is the expected increase in fertilizer consumption, and you see it's almost doubling. So fertilizer production, I have more competent people sitting down in the first row, and I'm sure that the panel will address it. But moving from the fossil production producing CO2 to a renewable energy line which is not emitting is the future. However, I take the comment, in all what I'm saying, we need to look at prices and the economics. I'll come to it a bit later, but let's look at steel. There are basically three phases of steel production. The first is the iron making, then the steel making, and then the finishing. The gray steel production starts with iron ore and coal, goes to BF, a blast furnace, and then in steel making, a blast oxygen furnace, and then comes the finishing part until you have the final product. You see the numbers on the right, energy use and CO2 emissions for gray, but also now for green. There, you bring together the iron ore with hydrogen in a direct reduction process, producing direct reduced iron, and that looks like DRI on the left. And the good thing is, if you have one more step, you have hot briquetted iron, which is very easy to transport, much easier than to have a ship full of stones of iron ore, and then another 3 ships with hydrogen, shipping the whole stuff to Hamburg, where I come from, and producing the first step of the production chain in Germany. Why on earth? Do the processing where you have the hydrogen and the iron ore and ship something like the hot briquetted iron. I'll not go through the details here, but this graph shows you that there is a win-win situation for both the exporting and the importing country. because it creates jobs, as I said, in the exporting country. In this case, it's 95 people per million ton of DRI. And yes, in the importing countries, you lose these 95 jobs. But anyhow, the steel production, it's the finishing part that makes the employment in Germany or in Belgium or wherever. So it's marginal, the loss in jobs. Whereas in the exporting country, you have not only more jobs, you also have more value added, and the steel industry in the European Union and in Germany will benefit because its costs will go down because you have a cheaper first step of steel making input. Yeah? So you're saving the competitiveness of your steel industry in, I say Germany, but I mean Europe, and in the exporting countries, be it Morocco, be it Mauritania, or Namibia, you have an increase in value added, the beginning of an industrial development process. So let's think more in those categories, and I can tell you, bringing such a graph to discussions with German trade unions in the steel industry isn't an easy job, but they get the message at some point. Let's move to another industry, and that is the shipping, the maritime industry. The graph shows how the global seaborne trade in terms of ton miles developed over the last decades. It has increased threefold since 1990. That's globalization of trade, etc. And it's expected to increase by another 30% until 2050. So it's really a growing industry. Interestingly, the greenhouse gas emissions increased in parallel with the trade until about 2010, and then it remained stable. Why? Because the shipping industry has really invested a lot in increasing efficiency in the shipping sector. So there is a kind of decoupling between the growth in trade flow, but obviously this is not enough. And there is the International Maritime Organization, which has come up with strategies how to reduce greenhouse gas emissions. And initially in 2018, the target was reduce greenhouse gas emissions by 50%. In already a few years later, 2025, the strategy aims for net zero by 2050. Now, to reach this, as I said, efficiency is always key. Try to improve efficiency. Lots of ways of doing it. Logistics and digitalization will help. A very effective thing is just reduce the speed. Don't go full speed. It saves you a lot of energy. And why can you do it? Because currently, what they do is rush and wait. Yeah? They rush and then they wait in front of the Panama Canal, the Suez Canal, the ports. So by combining digitalization, just-in-time arrival, etc., you can actually have a much smoother system. But to close this remaining gap, what you will need is green alternative shipping fuels. And that's a huge market. And that can be either ammonia or methanol. You will not use hydrogen. This shows the volume you need equivalent to the diesel you use currently. Pure hydrogen, unfortunately, needs a lot of volume. So you will have to cool it down to make it liquid. You have to cool it down to more than 250 degrees minus, then it reduces the volume, but still you have an issue. Ammonia, to have it in liquid form for shipping, you have to cool it down to 34 degrees. So you have an issue of storage. And this is exemplified here for ships, and you see the ship, how big the tank would have to be if you use the alternative fuels. But it is a general issue. I mean, if you have to store either hydrogen or ammonia in ports or wherever, you have an issue of how to store it. I'll jump to the next sector, and I need to speed up. That's why I will be short. This is the projection how aviation will increase over the next decades. There are different scenarios from ICAO, the International Association for Aviation. Even if you have an optimistic scenario of high efficiency, still this means doubling the consumption of energy in the fuel. I promise I will not go through this graph, although it's important, and if I would have a session on sustainable aviation fuel, I would have to talk you through this, but the key message is currently the upper part, biofuels, that's most of the alternative aviation fuel used. We don't think that this is a sustainable solution in the longer run. The basic should be power to liquid through electrolysis, syngas, Fischer-Tropsch, and that's the way to go. But the carbon dioxide, the question is, where does it come from, the carbon you need? And there, we probably for some time will have to use biogenic residues. So that we are talking about BTL or PBTL in order to get the molecules, the carbon molecules, to go for methanol and then process that further to SAF. There is an important element in there. For the synthesis on the right hand, for the refinery, you need big scale. Yeah? Here you are at capital costs of $1 billion and more. Whereas on the left-hand side, for collecting the carbon, or you could call it the carbon run, like the milk run where you collect the milk, that typically is a decentralized structure, and there you need several units that have much lower capex costs, and you collect the carbon to produce methanol, and then it goes to large scale. Interesting discussion, but I don't have the time to go into the details. The third point was energy security and resilience. I mean, you have all seen that picture now, and you know what it's about. Through the Strait of Hormuz, a quarter of oil trade that is shipped is passing or not passing. A fifth of LNG, a third of fertilizer. Plus, we could add, only recently I discovered that also sulfur, which you need in fertilizer production, a very high percentage is passing through here. And what has happened with the war on Iran, the Strait of Hormuz is currently almost blocked, and you have thousands of ships that cannot pass it, and the implications, we don't know yet what and how this will end. But Hormuz is just one example. We in Germany experienced the cut of Russian gas very immediately 80% of the gas from Russia in the Ukraine war, and due to the explosion of the Nord Stream pipeline, was just gone. And that really fuels the debate about how do we get more resilient and less vulnerable in energy. And I'm sure this debate will trigger the next discussion about going green. Those are just a few graphs showing the share of the global trade for oil, gas, and fertilizer, and the price increase we've seen in recent weeks. 60%, 100%, 30%. So this was my first part, and I know I cannot say this was the first half. The second half must be shorter, and I will have to rush you through those points, but I want to briefly touch upon the trends and technologies, the costs and incentives, and the standards and certification issues that need to be addressed. Trends and technologies, and we said exaggerated disappointment in our hype curve. Those are the recent numbers from the IEA, the International Energy Agency, and since 2021, we've seen a 60% increase in green and hydrogen production. On the right, the expectation to 2030 is a fourfold increase. On the right, this is electrolyzer installed capacity, that's not projection, increased 9 times since 21. The electrolyzer production capacity has increased 6-fold. So there is a pipeline that is developing. And also the technology development is speeding up here for steel making, for ammonia ship engine. I'm not going to talk you through the details. However, this is the graphic that is worrying, and that is the number, or not the number, but the volume of the offtake agreements and how that developed. And you see, really there is this hype curve, and it's dropping. So it's not technology. What matters is economy and regulation. Even if the economics are right, we need to get the regulatory frameworks right. And that brings me to costs and incentives. This shows the development of synthetic green jet fuel production. By the way, it's from McKinsey, and I know that we have an expert from McKinsey, or a former expert sitting in the room. Maybe he will correct me, but this was an assumption how the cost curve will go down, and it is expected to meet the fossil jet fuel prices in 2050. I made a box around the assumed oil price, and that was $70 to $75 per barrel. We are currently at above 100, and that shows how risky assumptions about fuel prices in the future are, and how quickly that might change. So, if the lower part of this gray part is the so-called aggressive cost reduction case, if we would manage to get costs down quicker, then you meet the fossil fuel price already in the mid of the 2030s. And now comes one point which I think we will need, and that is policy. If there would be a carbon price introduced, then the fossil curve would move up, and then you would move the time when you get cost parity with fossil alternatives really much more forward to even the end of this century, which shows policy incentives can significantly speed up innovation and transformation. Now, I cannot talk about all the possible policy options for how to interfere in markets. I just want to give you one example from a German scheme, which also the EU has now applied, and that is H2 Global. It's a double auction system. There is one auction where hydrogen or ammonia is procured from consortia of producers, and with that, they have a hydrogen procurement agreement for 10 years. So they know a supply price for the next 10 years. And on the other hand, you have an auction on industries and transport sectors that need hydrogen and derivatives. And those contracts are for 1 year. And you have the off-taker price, and no surprise, there is a difference. And that difference is actually paid by state intervention, by the German budget, by the European Investment Bank, or so-called European Hydrogen Bank. But the supplier knows for 10 years the price he will get. The demand-side auctions are yearly, and the expectation is that the willingness to pay will increase gradually so that the difference is getting smaller. That is one mechanism that I think could help in closing the price gap and speeding up the offtake. Of course, there are pros and cons, but interestingly, for example, ammonia production in Egypt, they won the first procurement auction with quite interesting prices, and I would wonder what OCP says, how viable this is, but I wanted to show the logic of such very quickly on standards and certification. Without clear regulation, standards and certification, nothing will work in the market. And for that, you need to move from sustainability and climate concerns to proper criteria and to certification. And that's one process. The other process is you have to have proper due diligence processes through your whole value chain. And that means risk analysis, risk management, and reporting. You have to involve the relevant stakeholders, and you need community participation and partnership, otherwise you run into big risks in your investment projects. You need grievance mechanisms where people can bring up complaints, whistleblowing, etc. So, on the one hand, you need to be able to label your product as green, as sustainable, etc. Create your premium label for your product, labeling the product. And the other issue is you have to check your chain and know what's going on in your supply chain. There are lots of standards and certification schemes out there. You've heard I worked at the OECD, so I cannot do without to talk about the OECD Responsible Business Conduct Model, but I will, in the interest of time, go not into detail here. OECD has done guidances for responsible business conduct for many sectors, starting with critical minerals, but also then agriculture, textile sector, etc. I'm desperately waiting for the OECD guidance on hydrogen and power to X. Unfortunately, it's not yet in the pipeline, but we could suggest that. I have, over the last 2 years, worked with 30 other experts in the German industry norm organization, DIN, to develop sustainability norms for hydrogen and derivatives. And you have the 4 dimensions here: governance, environment, social affairs, economy. I mean, just look into environment. You have greenhouse gas emissions, you have water use, land use, biodiversity, etc. So 4 dimensions broken down into 18 principles and a total of 100 indicators. This norm is supposed to be finalized next week. And that's important, and that's why I'm presenting it here. Then this should be moved to the international level, to the ISO level. And for that, it is not possible that Germany says, oh, we've come up with the ideal solution, please adopt it. So it must be shared by other countries. We already have Namibia, who agreed to co-chair this process in ISO. Well, we need at least 5 to 6 other countries to agree to actively participate in the development of this international norm. And it will look different from the current German draft. There will be China and India sitting at the table and discussing this. I can only encourage a country like Morocco that is so deeply engaged in this process. Come and sit at the table, because the standards and indicators that are developed there will matter for you. You have seen what's happening if the EU is setting its rules independently and you are struggling with implementing it. So I come back to the hype curve. The stages were, is it technically feasible? Is it economically competitive? And increasingly, I think you have to be sure it's locally adapted and globally coherent. And for that to ensure, you need international cooperation and partnerships. So I would like to see that rationale added to the 3 I have tried to develop here, and then my answer would be clear. Yes, there is a real future for green hydrogen and power to X in Morocco, but also around the world. And the International Power to X hub, where I come from, we stand for that, to help build such partnerships. And I'm happy to say that we have quite a tradition already to work with Morocco, but with 14 to 15 other countries. So let's continue in that spirit. Thank you very much.
So we still have the time for 2 or 3 questions again. And I was curious to learn whether you see green hydrogen becoming as a globally traded commodity like the LNG, or do you see it more as regionally anchored?
Yes, LNG is globally traded. I don't see hydrogen as a globally traded product as hydrogen. I see globally traded ammonia, I see globally traded methanol, so hydrogen derivatives. That's why I always say when we started, we considered calling us the Green Hydrogen Hub, and we decided, no, we go for the Green PTX hub, then people say, oh, what, PTX? No clue what that is. Basically, it is think beyond hydrogen, think in the derivatives that are really the products you want, and think not so much in a supply logic, so from hydrogen to ammonia, and think the other way around. What do I need for my country, for my industry? What do I really need the green molecules for? And so think in a demand logic rather than supply. So I don't see hydrogen replacing LNG, but I see LNG being replaced, maybe not tomorrow, but in the medium term, by ammonia and methanol.
Thank you, Professor. Do we have
And
any?
I'm curious to see what the experts from the industry will say if I'm completely mistaken.
Sure. Do we have any comments or questions in the room? Maybe to get back at what was shared by Professor von Meyer. Yes, we have a question there. Can we have the mic?
And I see a lot of young people sitting in the back, and I can only encourage you. This is an interesting area to work on and to study. I can tell you, 6, 7 years ago, I had no clue about all of this. So it's possible to learn about it and to invest, and I can only encourage you because this country really has enormous potential.
Okay. Thank you very much for this insightful and great presentation. So I have first a comment regarding, I appreciate your point of view regarding that green hydrogen. It's not like the molecule, the versatile molecule that can resolve all the problem or the issue to get net zero. It's one of the lever. Yes, we can use green hydrogen to make green steel, to make e-safe, to make green ammonia, but not, there is electrifying still have more potential for that. I have questions regarding, in one of your slides, you talk about the SDG, the Sustainable Development Goals, and why we are focusing only on carbon emission, and there are other SDG like poverty, like pollution and others. The cause is it's the priority. We have climate change, or there is another consideration. Thank you very much.
Thank you for that comment. It's running open doors with me. I have started in our PTX hub with working on the sustainability dimensions and criteria, because it is not just about carbon. And the first argument comes, yes, but water. Yeah? And you have to look into the water issue, and you discover, okay, can be solved. There are other issues. There are land use conflicts, but there are also social issues. Are people prepared? Do you have a workforce that is properly trained? And again, we've seen, yes, at the university level there is investment, but also at other levels. What are the job implications? I mean, I've been to Namibia. Big projects announced. 15 million people get employment. Yeah, to construct the site. Once it's built, there will be jobs for 3,000. So what's happening to the other 12,000? Yeah? If we don't develop proper strategies for jobs, for skills, for how to move the workforce, etc., we will run into big problems. That's why I had that plea, look at stakeholder participation, etc. So I have not shown my so-called EESG framework. ESG is quite known. It's environmental, social, and governance. We at the PTX Hub have explicitly added a second E because the economic sustainable development is equally important for countries. I had the privilege 2 years ago here in the Executive Master's course to give a master's lecture. I think it was 2 days about nothing else but sustainability, dimensions, etc. If you contact me, I'll send you the paper and the slides. You're right. Carbon is a major issue, but biodiversity loss and others are equally important. And that is why when we talk about biogenic residues as carbon sources, yeah, let's be very clear and look at what we mean. Yeah? You have in China so-called used cooking oil that is used to produce jet fuel. Well, it was not all used cooking oil. It was straight imported from Indonesia, where you had cut the rainforest to produce palm oil. So this kind of problems we need to avoid by all means. And by the way, there is enough residual carbon in most countries, and even if you only take sewage sludge from water treatment.
Thank you.
Thank you, Professor. Do we have any last question in the room, maybe? Okay, a last question from me. So to anchor back the question to the topic, how do you see Morocco's role evolving in the green hydrogen space, both as a supplier, as a partner? What policies could strengthen its role?
Well, I think I was clear. I see Morocco clearly as a supplier, clearly as a competitor, clearly as a partner, and we need to address this in partnership. And yes, we are operating in global markets where we are competing, and competition helps us to move forward, but that doesn't mean we should not be partnering in developing these these markets. Yes, we need to improve the policy instruments because the technology alone will bring down the costs, but maybe not quick enough. So for an intermediate period, we need, political support. Look at what China does. China is investing hugely in this. Unfortunately, my statement is the EU is not doing enough. Morocco, I think, is doing a lot, but as usual, you could do more and better, starting with developing renewable capacity. You have such an enormous amount, and I've seen Morocco from the airplane, I've seen it now coming from Marrakesh by car, and I was thinking, okay, there is much potential for more solar panels. If I go on a German Autobahn, I see more panels than here. Maybe you have them in other places that are even better than along the highway from Marrakesh, but I'm really convinced that there is a lot of space to improve.
Thank you so much, Professor. Thank you for all the insights that you have provided us with. And on that note, we move to our panel. Just so that you know, we have a coffee break outside. Please feel free to go grab your coffee, water, and come back in the room. We might get a 5 to 10 minutes break, and then we'll be back in the room. Thank you.
Thank you very much.
شد في يدي واخد اول أما الميكرو أنا خليه هنا.
So we have heard the science and the policy. Now it's time to move on to the execution. Transitioning from vision to a commercial scale reality requires a synergy between research, industry, and operations. I'm now joined by a distinguished group of leaders who are on the front lines of this industrial shift. So with no further ado, I would like to start by welcoming our distinguished speakers, starting by one that's leading the hydrogen and derivatives strategy for one of the world's largest industrial players, OCP Group. Mr. Til Zeino Mahmelet, welcome on stage. Next is a senior executive with over 25 years in power generation. He previously spent 2 decades at Taqa, Morocco, and now serves as the Vice President of Cluster Green H2. Country General Manager of Aqua Power, Mr. Omar Alawi Hamdi, welcome to the stage. Next is the leader heading the Research Institute in Solar Energy and New Energies, a central pillar for Moroccan innovation in renewables. Director of IREZEN, Mr. Samir Rashidi, welcome on stage. Our next speaker is bridging the gap between R&D industrial application. General Director of the Green Energy Park and Director of Innovate for Industry, Mr. Mohamed Bousta, welcome on stage. And our next speaker is focusing on the operationalization of green hydrogen projects. Chief Operations Officer at Hydrogel, Mr. Younes Farouk, welcome on stage. Thank you. And as you can see on our screen, we will be joined by our 2 previous speakers, Professor Abdsamad Fayek and Professor Heino von Meyer. Welcome on stage as well. So thank you to our distinguished guests for joining us for the panel this afternoon so that we could take the conversations further, complement and add on what was discussed earlier. Maybe we could start by speaking from your own institution's point of view and how are you concretely working on contributing to the realization of green hydrogen in Morocco, what operations are done and what efforts are made by your own institutions. Maybe we could start with you, Mr. Til.
Yes, thank you, and it's a great pleasure to be here on the panel today. So at OCP, I mean, we have a very holistic approach in what we do regarding green hydrogen, green ammonia, and then politics in more general terms. We think there's a great opportunity here for our company, for Morocco, but then also for international markets. This means we have an own offtake. We have heard about this. We've talked about this. But beyond this, we see it in a holistic way, meaning like beyond producing green molecules in Morocco, where there's a great opportunity that we see, it's also building ecosystems. Ecosystems meaning the development of technology, innovation, but then also offtake industries, and we heard it in the presentation before. It's to say also we can have develop industrial platforms that can bring local value creation and also additional offtake markets. And this is beyond, of course, like export opportunities to other regions such as Europe and beyond. So this in a nutshell.
Thank you. And from an Aqua's point of view?
Thank you first for inviting me to this panel. Thank you to UM6P for that. Aqua Power, just a presentation of the company. Company has 93 gigawatt of installed capacity, with more than 50% based on renewables. We are the first private company in terms of size on desalination, with 9.3 million cubic meter per day of desalination water, which is almost for 34 million people. And we are in the first mover on green hydrogen, with the landmark project like NEOM project, with 1.2 million tons of green ammonia that will be available by beginning next year. Already with offtake, and we have been one of the first mover on green hydrogen field. In Morocco, we have a presence with total capacity of 800 megawatt, basically solar and wind. And we have been selected and awarded apart the 5 consortium on the Moroccan green hydrogen offer. And for that, we want to benefit Morocco from our expertise and our project lessons learned from NEOM and from other projects, because we have also running project in Uzbekistan. So for us, these lessons learned can be shared with the Moroccan ecosystem to develop economically viable green hydrogen project in the mid to short term.
Thank you, Mr. Alabi. And from an Irazen's point of view, what efforts are deployed?
Thank you so much, Lila Kauthar. I would like to thank you, first of all, for the kind invitation, and also would like to congratulate the UM6P for this successful week, and for making it also a Sunnah Hasana, a good tradition that put people together, and we try together to abolish the walls and make innovation more open and more impactful. I would take the shortcut from the theme of this week's convergence. So what we try to do at Irazen as early as 2017 approximately is we cut the low signals from partners and networks, especially that was the report of the IEA in 2016, who has lit a little bit the bulb in our head, and from then we thought that it is really a good opportunity for our country to engage, at least from an institutional point of view, in this pathway. And then we went back to our DNA, which is tri-dimensional. We have a kind of first dimension is institution and policy. So we are backed by our Ministry of Energy. So we have we have a mission statement with them. We are also part of the ecosystem, especially with the industry, and would like also to support them in past the innovation in the renewables in general, but hydrogen in particular. And last but not least, the R&D and the applied R&D. And so what we have done, first thing was to support our government or our ministry to see the opportunity, both on the economic side, but also from the organization and strategy point of view. That was the impulse of the roadmap that was published back in 2021. And that was a pride for Irazen that was impulsed by us. And that was, let's say, the first ignition in terms of awareness. In parallel, also, we have been really honored to have been trusted by our colleagues from OCP to advance on a pilot scale unit on green ammonia that was then developed and taken over by our colleagues at UM6P. Sim Mohammed will probably have a word on that. And last but not least, we support the industry in impulsing the creation of the cluster, the green hydrogen cluster. So that's why we tried at least to pave the way. And as a catalyzer, we are still active in all those three areas that are defining our thing. Now, with our colleagues at UM6P, we're working on a green hydrogen application platform that will be a kind of not a copy-paste, but a kind of a duplication of what we have done in Ben Gurion with the Green Energy Park. So that would be our open sky lab to test hydrogen technologies on a megawatt scale. So that's one. And in parallel, we try to feed this platform, future platform, in terms of projects and ideas and pilot units. So we are still working on that.
Thank you. Thank you, Mr. Rashidi. And Mr. Busta, what about, from the point of view of the Green Energy Park or the Innovate for Industry?
Thank you, Kautar. So first of all, I would like to thank the organizing team for this event and also for this Science Week. So coming back to question, this first question. So for me, there is maybe 3 concrete actions we are doing. The first is building the Green H2A platform, which Samir talked about, in partnership with OCP and Erizen. So this is a platform with 15 hectares in Jolfsvar chemical plant, with the first pilot, which is the GAP pilot, green ammonia pilot plant, using 2 different technologies for electrolysis, 4 megawatts, alkaline and PEM technology, with 4 tons per day green ammonia synthesis using Haber-Bosch, with storage for hydrogen, storage for ammonia and nitrogen units, and with emulator to simulate any kind of profile, PV wind profile. So basically, first test we will do is using the Tarfaya of the south of Morocco profile to test this pilot and to have the first data coming from this pilot. So now, basically, we are in the construction phase, preparing the early startup of the hydrogen electrolyzers, nitrogen units, storage, hydrogen storage. The second concrete actions we do in Green Energy Park, for example, is we were working in R&D innovation in renewable energy with partners to provide the best technologies they can use to be competitive in terms of energy. I'm talking about this because when we talk about green hydrogen, green ammonia, means we are using green electricity. And this is important because 70% of the competitiveness is coming from LCOE, mean the cost of electricity, green electricity. And last but not least, actions is all that is linked to training in these technologies. Thank you.
Thank you, Mr. Busta. Mr. Farouk, what about the efforts made by Hydrogel for the green hydrogen in Morocco?
Thank you, Qatar. Good afternoon to everyone. Very happy to be here with you as well. Well, to answer that question, I would first say that our existence is in itself a good proof of what we're doing for the country for hydrogen. Hydrogel is a young company that has been created by Innovex, and it's playing the role of developer of green hydrogen and other derivatives on behalf of the OCP group. So obviously, the very known or so famous piece of work we're doing is developing the green hydrogen, green ammonia projects on behalf of the group. And there we are advancing the studies and preparing for the next phases of these projects. The other piece I would say, to make it very short, is the effort we're doing with the other colleagues here as part of the Moroccan Green Hydrogen Cluster, which is playing a key role in initiating and putting and bringing the debate about hydrogen and working on many initiatives to catalyze somehow the different pieces needed to bring the different pieces of the value chains to real life.
Thank you, Mr. Farouk. Professor Faiq?
Okay, from my side, I have a question to Mr. Haino. Today we are very happy and lucky to gather all the main players that we have here in Morocco working on to develop this emerging field of green hydrogen. It's supposed also to be with us Reda Hamdoun from Nariva and Hamid and Nofel Fadili from Mazen. Unfortunately, due to the last moment's engagement, they apologize to not come here. My question to you, how you see this initiative in Morocco, how you see the involvement of these main players, stakeholders, industry to develop green hydrogen. And from critical point of view, if you see that still missing like a piece of the puzzle that we should target in Morocco, or everything is complete and just we need to hurry up?
Well, difficult question, but I can really honestly say, looking at Morocco, and we at the PTX Hub have from the very beginning had a close eye on what's going on here. What is impressive is that there is already the bringing together of stakeholders developed far more than in many other countries. I'm sure that I didn't have it on screen, but in my hidden slides in the presentation, I had a picture of the hydrogen strategy, which is also called the PTX roadmap, and which has the logos of at least 5 ministries on top, which already shows it is not just an energy exercise. It is really an undertaking that is bringing to the table all different players. And for sure, that's not always easy, and there are conflicting interests, of course. But those are very important steps. Many other countries are still far behind that. I'm just another example. I mean, I'm working in other countries on green shipping to bring together the maritime community and the energy people to think about the strategy. Oh, that takes ages. My impression is in Morocco, the level of debate, and I think this panel is really impressive. The expertise that you have gathered here, and you coming from different backgrounds, and for sure you may have different opinions on some points, but there is a culture of exchanging on the subject, being honest about the difficulties, and communicating them. Communicating with policy isn't always easy, we know that, but I think the current context is pushing the stakeholders to speak with one and not with 6 voices. How many are we?
Exactly 6. So we have spoken earlier about at the lunch table, we were speaking about the financing of the projects. And so I think we could start from this point. Globally, and not just in Morocco, so many hydrogen projects are announced or defended, but not as many reach the final investment decision. So maybe I'm going to start from an aqua point of view again with you, Mr. Alawi. What factor or factors prevents these projects from reaching this investment decision, final investment decision?
Okay. So it's not a technological issue. It's about bankable offtake and the long-term offtake, a certainty about regulation on the long term, and large and integrated infrastructure, both on the electron side with large size of renewables, be it solar, wind, coupled with battery storage, grid infrastructure, storage infrastructure, and transportation infrastructure. So all those elements are the main, today, blockers for this project to reach FID. But one of the biggest one is, at the end, bankable offtake. And for that, we need to give clarity on the long-term view in terms of pricing. The good thing with also green hydrogen, we know that the green electron will represent 60% to even 65% of the total cost. And when we have, like Morocco, very competitive capacity to produce the green electron at low cost, this has given us interesting competitive advantage. The location of Morocco also close to one of the biggest market, which is Europe, but also our domestic market, it's at very important enablers to move to project that can reach FID. The other element is to make sure that we have the public and the private players working together to find solutions. And this, we're doing that through maybe this discussion today, but also in different forums where we have a private and public discussion together how we can solve the blockers and the challenges and move the challenges to an opportunity. Now, this market is starting. It's a new market, a new technology coming to the world, and we need support. We cannot say that from the beginning, if we start thinking that we need to add royalties on the green hydrogen, will not serve the purpose. It's not like we discovered an oil field and we need to have royalties on oil field. It's a different world, and we need to help and support this new technology to start. And once it becomes mature, we need to discuss how we can benefit to the local, I would say, host countries of the benefit of green hydrogen. So this is one of the elements we should not mix between green hydrogen and we found the new oil market. It's not the new oil. So to be true, it's something different that need to be encouraged to reach maturity. Another maybe point is to move to FID on this project. It's important to have clarity on the regulation on the long term. Local regulation, but also regulation in the worldwide, especially in the market where we expect that there will be 10 million tons of import, but at the end we discover, due to the regulation restrictions, it's becoming a niche market. And this cannot be sustainable for banks that will bring financing on the long term. And we need to think about also innovation on the financing. We cannot have only a type of project finance that like we used to have for utilities. It's different. We need the blended financing. We need to innovate on the financing of this project to make sure that at the end we came with a solution that is appropriate for the green hydrogen market.
Yes, clear. And you've mentioned a critical point, which is the off-takers, especially speaking about the global markets. So maybe with you, Mr. Zaino Mahmalet, how critical is it to have these global off-takers to develop the projects, and how risky is it if the demand develops slower than what's expected initially?
Yes, thank you. And I'll build a bit on what my previous speaker said. I mean, bankability is critical. I mean, it's absolutely necessary to build a project. I think there was part of the hype we heard about before. In this hype phase, everyone was thinking, okay, the financing would be very similar to financing a renewable project. And the truth is, it's not the case. It's different. It's a different product. It's a different market. So, and at the end of the day, green ammonia or green hydrogen, no matter which derivative, I would believe to be a commodity. At the end of the day, there will be competition in a commodity market. So, the cost point and the price point are very relevant. So, to your question, I mean, it's important to have bankable offtake, to have project finance at least to a certain level, and to reduce cost. Because beyond as it has been said, the cost of the electrons is critical. It's a huge component of the cost. At the same time, financing cost is also an important cost point. So there is a need for offtake agreements in export markets. We have the opportunity, of course, to locally offtake as OCP, and there might be, I think there will be other offtake markets also in Morocco for other users. But it would be a mix. I mean, it would also be export markets to be addressed, as well as local offtake for fertilizer production. So there is a huge impact on the regulations, and also in, for example, the European market, and how this market would ramp up over time. and which kind of long-term offtake arrangements could be made.
Thank you. And Mr. Rashidi, from your point at Yarezen, same question about the off-takers and how critical their role is to the global or the international expansion.
I will take the researcher hat to be a bit free in expressing myself. Well, what I think really is that when we supported the elaboration of the roadmap back in 2021 with all the stakeholders, one piece of the assumption was that in terms of offtake we have a kind of Pareto, 20% domestic and 80% somehow at exports. But now what we are seeing, and I think Heino has illustrated this very well in his slides, is that we see that there is a lack of order. I mean, the European market, which Siamar has spoken about, is lacking a little bit momentum. Not necessarily because there is no vision, but because there are new let's say crises that a little bit disturb the equilibrium. So we need to, in my opinion, we need to have a frank discussion. Are we true or are we serious? Let's say, take it like this, about this energy transition or this climate change fighting. And as I say every time, for this to be deployed at scale, we need a planet alignment. I mean, not only public-private, we need research, we need local authorities. This is a big issue. And about the competencies in Dakhla, in Oriental, etc. We need really a planet alignment, and therefore we need everyone to be aligned before that. And in my opinion, what we are lacking now is this alignment. We went very, let's say, enthusiastic at the beginning, and now we are a bit not frightened, but let's say cooled in terms of thermal engineering when we see those kind of assumptions that are changing. So what we need is, first of all, as we consider, for example, the Moroccan ports as European ports, and they should apply by the CBAM or carbon taxes thing. We need also to think of Morocco as probably an extension of the European territory as a project development place, and to treat projects, especially first movers. I'm not speaking probably about all players, but I think, in my opinion, they deserve, as Alawi said, a kind of a push. Would it be subsidies? I think, in my opinion, it's better or it's easier to subsidize a Moroccan project or a project in a very positive or a context in terms of solar resource, wind resource, and cost of hydrogen. Let's say, I don't. Please don't take it as a reality what I say. But let's say, for example, a European bank are speaking about prices around $6 to $8 per kilogram or euros per kilogram for hydrogen. In Morocco, in my opinion, there is no project yet, but in lots of studies, we are around, let's say, 3. So I think, in my opinion, and from a financial point of view, and also from a regulatory point of view, it's easier to subsidize a price or a project that is near to 2, which is the dream or the target price, than to subsidize €8, just because we need to have a kind of a rationale for some political perspective or some ideologies, etc. So we need to be really very pragmatical and to say, okay, if it will happen here first, and then I think, in my opinion, with those first movers, we will draw the learning curve down, and then the cost even for the sites that are northern to Morocco or even southern to Europe will be probably lower in cost, and because the size of the industrial scale will and the learning curve will go down, as we have seen in all technologies. So, in my opinion, there is a big, I don't know how to say it in English, un dialogue des sourds. We all know what we should do, but no one is pointing things, because now priorities are somewhere. Each country is focalized on its priorities. The Ukraine-Russian crisis was a big shake, I think, for the EU, and now we think in the Middle East things are not having a nice perspective. However, this could probably push the rationale of having resilience in terms of green fuels in the Mediterranean basin. And last thing, to finish on a positive note, sorry to have disturbed the morale of the audience. I'm sorry about that. But a positive aspect that I see is that China last week or 2 weeks ago have made, and this is really, I think, the best news we have as hydrogen followers or at least experts, is that China has made green molecules, especially green fuels, a national priority for its 5-year plan. So in my opinion, in less than probably 5 years, as the Chinese do, they are always ahead of schedule of their 5-year plan. I think we will see a ton of methanol or ammonia, if not lower than the fossil one, probably at least at a parity, in my opinion.
Yes, thank you again for reminding us of how the challenges happening in some region of the world still impacts the rest of the world, and how each country having their own priorities impacts the alignment regarding the green hydrogen and every other topic. Maybe I'll move back to Mr. Farouk about the situation here in Morocco, and from your own perspective, what does it take to unlock a large-scale deployment first here? Because Mr. Alawi said that the problem is not really the technology. So do you think it's technology-wise, infrastructure, financing, regulations? Where do you see it? What does it take to unlock that?
Look, yes, I hear the challenge from as well from Samir, who's putting new targets here, which are more than welcome. Now, back to your question. To be honest, I would say the three of them, you can't take these elements in isolation from each other. I think that it's a combination of both, but what you can consider and say, yes, between technology, financing, and then regulation, some of these elements are or do stay under the control of project developers, while others are a kind of being imposed on these players. So, like said by Alawi, technology for me is I would say for most pieces of the value chain is already mature, and even to a very good extent when it comes to electrolyzers. So it's not a story of technology. For financing, there are today a lot of good structures that allows you to work on your financing and help your business plan to get to good ballparks, I would say. Yes, there are still some bankability challenges, but even these, to be honest, once you have moved through 1, 2, 3 projects, you build the track record and you will get these behind you as well. The story of regulation is a different story. There, what happens is that we are still in a space where the rules are, I would say, rather unclear, not to say still blurry, not very stable, which brings a bit of uncomfort to sponsors, to lenders, to any potential investors, because these rules actually could and do sometimes, when they are structural in the shaping of the projects, impact the lending costs of these projects. So you can't develop projects and making structural decisions while the ground is somehow still moving. This is what... Actually, look at what happens very practically speaking. In Europe, there are some rules for what we call RFNBO hydrogen. If you look at how these has been translated, or if they were translated to country binding rules, it has been the case for 1 to 2 countries at max, which means that you are still developing projects for a market that is your fit for purpose market, in which the rules are not very clear, which doesn't help that much in making or progressing your projects. Beyond that, I think that we feel that in terms of even stability, Europe is facing some job and sovereignty discussions. So we are even considering some of these rules to face the economic position of the continent. So all of this is not serving that purpose. But look, I think that some good debates are happening today, and I stay positive and believe and hope at least that, like said by Samir, if we are very serious about this transition, we need to make some cut decision very quickly to allow this industry to kickstart.
Right, and since we are speaking about sovereignty, and very often we hear the speech about Morocco or Africa overall as just exporters of green molecules. So my question would be to you, Mr. Busta, about how do you see what can we do to make and build a strong local industrial ecosystem? Speaking of manufacturing, IP maybe, what efforts could be deployed to strengthen the local industrial ecosystem?
Thank you, Kautar, for this question. So I will not maybe repeat what has been said, but I agree about to unlock projects. We need, of course, offtake and bankability of a project, to have also incentive and a clear offer. I think it's what we have in Morocco since March 2024. We have a clear Moroccan offer, which has been weighted from I'd say industries to provide and their projects and to propose their projects in Morocco. Now, since 2024, things are clear. I think the offer is clear in terms of incentive, in terms of land available for developing this sector of green hydrogen, upstream and downstream, means green electricity, but also application of green hydrogen, means ammonia, power to liquid, and other application of green hydrogen. So I think that this is key for me this is key for the development of this sector. Now things are clear. I think we have a first wave of projects we have seen during the presentation in the beginning of this afternoon, that we have five projects, $32 billion investments. We have also one leader, which is OCP, and which is playing the role of locomotive in this development, because these investments which has been presented and engaged by OCP is not for doing export, but it's first for decarbonization of its operations, and to achieve these objectives. OCP need to produce green ammonia, because as you know, OCP now imports 2 million tons grey ammonia, and to achieve the objective of neutrality in terms of CO2 emission, we need to produce green ammonia locally. So I think now we are in a situation where Moroccan offer, a clear Moroccan offer. We have a locomotive which is pulling, let's say, this sector. And in terms of key remaining points, I think it's how we can be now work in the competitiveness of this sector. And here is we are making the link, let's say, with R&D and how we can develop our IP, how we can work on R&Ds and innovation in all these technologies, from electrolysis to aborbor synthesis to materials. Also, it's also key materials we need to work on and to find some innovation to decrease the price and of the equipments and improve the competitiveness. So I think now we are really, for me, we are nearly in a situation we have the ingredients, but we need to accelerate things. That's it. Thank you.
Okay, thank you very much. It's clear from all the speakers that we have one of the bottleneck is the off-taker. And my question to Professor Heino, because we saw in the last years that we have many initiatives, mainly coming from Germany, to support the deployment of green hydrogen in outside of Europe, and even that some news coming that the signed agreement with Egypt as off-taker of green ammonia. This was a great news, but when you go to details, is a short-term contract. That means, okay, for me, my question, like this kind of individual initiative from Europe is not able to accelerate these developments. What about the future? If these kind of initiatives will be evolved to some joint initiatives from whole Europe to support the deployment of these green molecules in general, because at the end is also question now, when we are living in this kind of crisis nowadays, I think this initiative should be started long time ago to mitigate this kind of crisis that are happening now. What is your opinion?
Well, that's a very difficult question. I mean, talking about the German situation, you are aware that we had change in government, that the emphasis is shifting currently, let's say, away from renewables back to gas. But on the other hand, I'm still pretty optimistic that the market will clearly show the signals and the prices for renewables are getting into an order of magnitude where it's simply an economic interest that's driving the market, and a lot of ideology can be forgotten on renewables. On hydrogen and derivatives, yes, we're facing difficulties but again, I fully share the view that in the regulatory context, huge mistakes were made. Maybe in the best interest, and I would still agree that additionality is an important issue, that we should not take renewable energy away from the transition and from the supply to normal people and use it for hydrogen and then through the back door have fossil energy in. So I think on additionality, there is a good argument. But when you move further into issues of temporal and geographic correlation, etc., there I think, not only I think, Europe has imposed European concepts on other countries, and that should not happen. Issues like it must come from the same bidding zone, the electricity, that's a concept that works in the European market. And I've worked in India, and people in India say, sorry, I mean, we are India, and that's one bidding zone. We have an integrated market. What do you want with these concepts? Yeah. So there is an exaggeration, yes. But now it becomes even worse, that there is a debate on how to improve it, but not clear how it will be improved. So again, the rules are not clear. And as an investor who, as you said, doesn't know exactly what the rules are, even if they are bad, but if there is a debate we will change the rules, yeah, of course, they will wait. So, sorry, I'm going too much. I wanted to pick up one aspect. Let's think about innovative finance. Innovation not just in technology, but also in finance. To some extent, maybe this double auction mechanism is one element which I presented, but you're right, the agreement for the suppliers is for 10 years, and 10 years is not enough for the investors, at least in this moment. But there are other elements, and I think we need to think much more about guarantees. The state should guarantee. That doesn't have immediate budget implications because additional money in the budgets in Europe and in other countries are difficult to find. So find a way that the public sector can produce security without using public budget money. And there, I think the whole issue of guarantees is something to look at.
So we agree that the most critical and important part is bankability and financing of these projects in all options that are available. We've mentioned off-takers and others. Maybe I'll go back with you, Mr. Alawi Mhamdi, about the Moroccan offer. From an investor's point of view, what do you think is the most attractive asset within that Moroccan offer?
Okay. So for the Moroccan offer, give at least clarity on the regulation. We have clear stakeholder, which is Mazen, to negotiate all the contracts. So this is allowed to improve in efficiency in terms of time and also in terms of potential and clarity about the process. And also the allocation of land, which is very important. So reservation of land, allocation of land, and also the fact that the Moroccan offer gives clear ability to discuss with all the ecosystem, be it private, public, to move forward on this project. So the Moroccan offer is give a structure. Now we need also to have a capacity to build large-scale infrastructure. And for that, we will need expertise. We need also a knowledge from previous experience. And for that, this is why Aqua Power can bring a differentiator here. We are building one of the biggest large-scale green hydrogen project with NEOM project. It's 4 gigawatt of renewables, 2.2 gigawatt of electrolyzers and 1.2 million tons of ammonia, green ammonia, with just the process area is 8 kilometers square of process. So building this large-scale industrial complex integrated with renewable, we need this expertise. And the Moroccan offer for the moment give the ability at least to start with the first part, which is producing green electron. Now we need to integrate this with how we will export green molecule, which is different. So we need to understand how we will move from green electron that we used to do it. We have plenty of experience now in Morocco. How we will be developing the green molecule, how we will export the green molecule, how we will build the partnership with ports in Morocco and in Europe and elsewhere also. So those elements still to be developed are very important. And we have also the local anchor, which is OCP. And you are talking about this 20-80% Pareto that was starting point. Maybe we can move from that to something 50-50 to move to something that is realistic on the short term in order to be able to have something important for Morocco, which is security of supply and sovereignty. So that's why very important to start by one project, help one project to be on the field, moving forward. And this is a choice at the end. Are we choosing to be on the forefront of this project or on the back seat and wait for the others how we'll be doing this project in the future?
Yes, it's definitely two perspectives and to each the results that come with it. And since you've mentioned green ammonia and the group OCP, my question to you, Mr. Zaino Mohammed, how can the green ammonia transform your business model overall from maybe from ammonia import to integrated energy, chemical, energy leadership?
Yes, I mean, one thing is, of course, like the decarbonization of our products, the fertilizer products that we produce over the complete value chain of fertilizer production. It includes our operations for mining and then fertilizer production. But then, of course, we have the green ammonia imports, ammonia imports. They're not green yet, of about 2 million tons. So there's a huge potential to decarbonize by producing green ammonia locally. This is one thing. Another point is, and has been discussed before, this question of resilience and change and volatility in markets. So there's an opportunity to de-risk actually our supply chain, right? I mean, importing ammonia and other raw material, I mean, there are huge fluctuations in the markets over the last years, and we expect them to be, well, it will rather continue this way than going back to normal as it might have been over the last decades. So there's an advantage of like de-risking our supply chain, and this can justify also like a local production and improve this. At the same time, of course, we have to look at economics. When we produce green fertilizers or decarbonized fertilizers, they address certain markets where there's value being created from those products. This could be the European market with CBAM and other mechanisms. But we also see opportunities in other regions of the world where producers of agricultural products look for decarbonized inputs because they want to produce, let's say, agricultural products that are decarbonized because they see markets for this, right? And it's really like, if you push it all the way, I mean, if you're a consumer and you go to the supermarket and buy a package of some food, and it could be, I don't know, a loaf of bread, it could be whatever, like noodles or vegetables. I mean, at the end of the day, if the consumer is willing to pay an additional few cents to buy a decarbonized product, and the share of the decarbonized fertilizer compared to not decarbonized fertilizer is very tiny, right? So it's the way how you can create, how do you bring down the value across the value chain. That is not in place today. This is something that we work on as OCP, and there are other players that look into this. So it's really like changing our value chain from end to end, and green ammonia is one part of it, right? And it's decarbonizing product, but at the same time also de-risking, let's say, our supply chain.
Mm-hmm. And speaking about this supply chain, if there is one product, especially hydrogen product, that Morocco could be known for, what would it be?
You mean in terms of derivatives? I mean, ammonia is probably the first product that makes sense for several reasons. I mean, you have it's transportable. I mean, it can be easily shipped, and we're one of the largest importers, so we handle it on a daily basis. We have a local offtake, and the other point that was mentioned, it can also be used as a marine fuel, so for shipping. Morocco is very well located on main shipping routes in the world. Just looking what passes by in the Strait of Gibraltar. So once this market for marine fuel kicks off, we see a huge opportunity to use also ammonia, green ammonia, as a marine fuel and an additional market. And in a later stage, you can think about other products such as e-methanol, e-methane, but then there you have the carbon question. You need to like a source of biogenic carbon, which is, well, it's another topic, but it's a more tricky question.
Yeah. And Mr. Bousta, also same question. If Morocco were to be globally known for one, maybe hydrogen technology, what would that be?
I would say maybe electrolysis technology, because it's the technology from where everything is starting, because we are talking about developing the sector upstream and downstream of green hydrogen, and the technology of electrolysis is maybe key. But I could say that ammonia also is very important, and the technology of synthesis of ammonia, for me, it may be also a second key technology we need to work on and to develop to have our own IPs and again to work on innovation. For me, if we want to succeed in the development of this sector, the key points, we have talked about many factors, but one key factor at the end is what we are talking about industries. And the key objective on an industry is to be competitive, to be competitive in its market. And competitiveness is R&D, is research, is innovation. So I think one key actions we need really to work on, to invest on, is how we can develop, how we can invest on innovation, on research, how we can give the possibilities to our PhDs to develop solutions, local solutions, to provide local innovation, and to serve and to work in partnership in these industries, in the companies, with the companies, to develop this partnership between research, education, and industries. And if we see in other continents or developed countries, the success, one key success factors is this one. How there is really a strong partnership between industry and research, education. And I think this is maybe one key actions we need really to focus on, is to invest on the future, and the future is students, is research, is innovation.
Exactly. Since you've mentioned education and research, what do you think maybe some of the challenges that block this taking it from the research to scaling it?
I think when we're talking about research, it's a question of financing. It's a question of money. Research needs money, needs investment. But I think this is a strategic decision we need to decide. Do we want really to invest on what will bring added value to the country tomorrow? We need to invest in. Today, what we see is you have one country now which become a leader in industry, in economy. China. China now is the first in terms of maybe in the economy. We've become more competitive compared to US. Due to what? One key factor is innovation. When you see the publication, now China is publishing more than US. So I think this is, again, just a decision, strategic decision. We need to decide and to allow this, again, in the universities, to reinforce this between universities and industries, to work very closely in terms of in partnership, to have more projects, to finance this project, because at the end, this is the industry which will benefit from that, and at the end, this is the country which will benefit of this investment.
Yes, and we see the efforts deployed by Morocco to boost the innovation and take it to the next level. So maybe we could try one final question to all our panelists and go back to the initial theme of our afternoon. Is there really a bright future for green hydrogen in Morocco? So maybe we start with you, Mr. Zaino Mahmelet.
Yes, thank you. The clear answer is yes. I think there is a bright future for Morocco in this emerging industry. Do we know the path exactly? We do not. I think there are huge opportunities, and it's up to us to see how to seize them, right? And there's local opportunities, there are export opportunities, there's the ecosystem question. And I think what I hear from the panel also, I mean, there's a strong alignment on those topics. I mean, saying that it's not only producing green molecules, that's obviously what we aim for, but it goes beyond this. I mean, it's establishing innovation, establishing local manufacturing, industrial platforms. So all this comes together. I think there are I can speak for OCP's projects. I know for other projects. I mean, they're all like in the starting blocks, and I think it's more a question of like when things will accelerate than anything else. So I remain very, very strongly optimistic.
Thank you. Mr. Alawi Mhamdi.
Morocco has a unique opportunity here, for sure. We have one of the best renewable capacity location, close to biggest market, political stability, and we have been able to deliver a large-scale project in the past. So, plus the human factor, and we are here in UM6P, we have engineers, we have all the knowledge to develop this project. So for sure we have unique opportunity, but at the same time, this is conditional to bankable project, innovate in financing, and make choice about do we want integrate this green economy or wait until this green economy will mature and start the process. It's about political choice at the end, but I think there's clear direction from the highest level of Morocco is to move forward in this green economy, and this is a big game changer.
A big sign that it is a green and bright for your future. Mr. Rashidi, what about you?
Well, even if I was a little bit pessimistic previously, but I would say also bright for the same reason my predecessors have mentioned, because I think if green hydrogen will happen, it will first happen in Morocco, or countries similar to Morocco. But this is also my subjective part. So I hope that it will happen first in Morocco because of what has been said before. However, in parallel, what I want also to convey as a message to the audience is that we are already doing things and concrete things, as Si Mohammed has mentioned, and probably as you have seen all this during the Science Week, what is happening in the labs. So what I would say from an innovation point of view, we are climbing the ladder of TRL, of technology readiness level. We have things that are happening in the labs. We have calls for proposals, both by Irazen but also other actors in Morocco focused on hydrogen. We have universities that are part of also of a research program, Horizon Europe, etc. And thanks to infrastructure like we are developing with UM6P at Green H2A, we have another, let's say, climb another ladder of the megawatt scale. And what I want also to convey as a message is to invite, as we need to, as Mohammed said, to innovate as an ecosystem, not delegating innovation to university or academia. We need the insights of industry and developers and technology providers to be in an accelerated pathway, to accelerate the progress. Because if we leave everyone in its own role, things will not happen. So we need to be on a fast track in terms of innovation. And this, for this, I would like also to convey a message to our developers and industry that are here, but they all know about that, to be part of our projects within the green hydrogen and application platform in Jorf. We have already been, and we are supported by the OCP group and the ecosystem, but we are also open to national and international developers to put the bricks, test technologies, de-risk large projects, and probably second iteration will be not the megawatt scale, probably tens or hundreds of megawatt scale, and then to the famous gigawatt scale we were speaking about years ago.
Thank you. Indeed, innovation doesn't happen only in the lab or among researchers, but it's everyone's role to innovate in their scope. Mr. Busta, what about you? Do you think that there is a bright future for green hydrogen in Morocco?
Yeah, Kautal, but I think after the presentation of Professor Fake and the answer was clear. It was yes.
We're just keeping the momentum positive.
Well, we have a clear presentation. We released some key insights about this subject. But I maybe just would like to add some points which are to me very important. To me, we are maybe in the situation where we are in if I maybe to make just a comparison with GSM and smartphone, it was really a game changer. At that time, when we have the first GSM, it was an innovation which changed the world, because it allowed some countries, which was a very low infrastructure for connecting and for telephone, to bridge the gap and to introduce this innovation and to have a connection and to be able to have calls and to bridge the gap in terms of technology. We are now in the same, for me, in the same situation. We have the opportunity now with green hydrogen and its application to be in the same opportunity and it's a game changer for Morocco. We are now we have the opportunity to change from, again, energy importation to be in the situation of energy producer. And when you see, and after the presentation we had, which was very clear, energy is a strategic sector. Energy is key for countries, and we have a very huge potential in terms of producing competitive electricity, green electricity, that makes Morocco in a very good position to be a great actor in this green hydrogen and its application, and it will change the country. But for me, we need maybe to accelerate things, because now we have really the good ingredient, as we said, in terms of offer, in terms of actors, in terms of maybe of infrastructure. We need to accelerate and really use this unfortunate situation in terms of war in the Middle East to just remind that sovereignty is priceless.
Indeed. And especially in the current context of unpredictability, speed is a key factor to move things forward and reach these common goals. Mr. Farouk, where about you?
This is a piece of excitement. Look, like it's been mentioned, I think we have the right recipe, we have the right ingredients, and we've been blessed with truly exceptional natural resources. And we have the right momentum, which we need to keep to make it very concrete. Yes, I am a deep believer that we are well positioned to make it happen. And to be very concrete, like I said, if you look at our projects, those that we are developing today, since the start of the journey where we started from almost nothing because it's a completely new piece of work, the progress is tremendous, and what we are able to achieve while putting the right effort into developing these projects is just encouraging, is massive. So yes, I believe we have a bright future in front of us.
Yes.
Okay.
Thank you.
I know. I guess that you answered the question during your presentation. I will give you another question, because I will ask you as with your heart of GZ, okay? We know that in Germany you have a very rich ecosystem that was developing this green hydrogen innovation during the last years. And now you mentioned that you have change of the governments, and this can be like an opportunity from Morocco side, and also here in Morocco we are doing things. This can be also an opportunity from Germany to see that there are a market that now is growing in Morocco. What is your recommendation? How we can get benefits of this kind of situation, the change happening in Germany, what's going on here in Morocco, to construct a solid partnership, Germany with Morocco ecosystem?
Well, thank you. That would have been my closing word anyhow. I had given the answer yes, but my last slide said what we need in addition is cooperation, international cooperation and partnerships. And there I see great potential. You mentioned it. I mean, there are lots of small and medium-sized companies in Germany that are experienced in manufacturing and establishing things, and there are, with the huge potential in this country, I think there are really serious opportunities, and we need to find the formats to organize these kind of partnerships. And that, for me, would have been my final message anyhow. I mean, I've worked 3 decades for the OECD, international cooperation and development. I'm fully convinced that approaches and multilateralism still in difficult times is the way to go and will be to the benefit of both sides. And I think Morocco really is a great potential partner.
Thank you so much to our panelists and our speakers for your insights. It's very clear that Morocco is now ready and positioned to be contributing to the discussions and to the transactions happening around green hydrogen amongst other industries, and be it whether on the technology, the regulations, the financing and the bankability, especially that we have mentioned as very important factors. Morocco is ready and taking actions that are aligned with the priorities, trying to put the efforts on a fast track to get to the wished and to hoped for results. So thank you so much, our dear panelists. I don't know if we have time to take questions, but we can see if we have 1 or 2 questions in the room very quickly. There is a question down here. So maybe we can take 1 question.
It will be a quick question. Quick 2 questions. First question for Mr. Alaoui. As you are close to the NEOM projects, I think this one can serve as benchmark for Morocco. And one of the important parameters for implementing the projects is the take-off agreements, the agreements for take-off. So I will not ask for the details, but which kind of industry have been keen to sign this kind of take-off agreements? So this is the question. Okay. So and for Mr. Mahalat, I would like just to have some information about your competitors. Do you know what are they doing, and mainly concerning Yara, who is the biggest actor in ammonia field? How are they progressing in the field of green ammonia?
All right, so I'll start. So on our competitors, and you speak in particular about Yara. I mean, Yara, they also, and it's not for me to speak to them, but what we understand about what they aim to do, they also look into decarbonizing their production, but they want to do it also only maintaining profits, so they don't want to have any losses here or any impact, and they do not aim at investing directly into green ammonia projects. So they're looking rather into off-taking green molecules, let's say, or green or blue molecules, but they have a very different starting point compared to Morocco, right, or Morocco at OCP. I mean, we're in a situation where we do have great renewable resources, which actually allow us producing low-cost green molecules, which is, from my understanding, not the case for Yara, that have a different context. And we don't have, I mean, in Morocco, we don't have any oil and gas legacy, right? So we're not stuck with sunk cost in multi-billion-dollar oil and gas projects. So we don't have this on our shoulders. So actually, it's a much better starting point to say we invest into green energy and green molecules.
Okay, for the offtake on NEOM green hydrogen project, just maybe clarification, this has been co-developed between Aqua and Air Product. And this is also some of the innovation that should be done for similar project is to have the off-taker with you as a co-shareholder. This is the risk somehow the project. So it's very important to innovate, and I'm sure that with the presence within in the local ecosystem of OCP, similar cases can be developed to emerge as a new green hydrogen project from Morocco.
Thank you so much, and I think that's it. Thank you so much, our panelists, for joining us, and thank you for your insights, and thank you for all answering yes to a bright future for green hydrogen for Morocco. That keeps us on that helps us end on a high note and keeps the momentum going to bridge the efforts and make sure that we all work together to make it happen. So I think we're just gonna take a group picture and yeah, before we go. Okay.